Picture yourself standing on a cliff that overlooks not the familiar patchwork of continents we know today, but something far more extraordinary. Below you stretches a single, colossal landmass, a world continent so vast that its opposite shores lie beyond the curve of the horizon. This is Earth as it existed 300 million years ago. This is Pangea. The wind carries with it the scent of unfamiliar vegetation and the distant rumble of geological forces that dwarf anything in our modern experience. There are no Atlantic or Pacific Oceans here, no Mediterranean Sea dividing Europe from Africa, no English Channel separating Britain from France. Instead, one unbroken expanse of land dominates the planet's surface, surrounded by an endless ocean that stretches to infinity in every direction. This is not the Earth of our ancestors, nor even the Earth of the dinosaurs as we typically imagine them. This is a world that predates human civilization by hundreds of millions of years, a world so alien yet so fundamental to our existence that understanding it requires us to abandon everything we think we know about geography, climate, and life itself. The name Pangea comes from ancient Greek, meaning all land, but this simple translation fails to capture the profound implications of what such a world would have been like. Imagine weather systems unrestrained by ocean barriers, storms that could rage across continents without interruption, and creatures that could walk from what would one day become New York to what would become Beijing without ever crossing a sea. As you stand on this prehistoric cliff, the sun overhead is the same star that warms our faces today, yet its light falls upon a planet so transformed that it might as well be an alien world. The very air you breathe contains different proportions of gases. The magnetic field that protects the planet flickers and shifts in patterns long forgotten. And beneath your feet, the ground itself moves with a restlessness that will, over millions of years, tear this unified world apart and scatter its pieces across the globe. Scientists tell us that Pangea existed. They can prove it through the careful study of rocks, fossils, and the gradual drift of continents. But knowing that something existed and truly understanding what it was like are two very different things. What did it feel like to live in a world where you could theoretically walk from pole to pole without crossing water deeper than a river? What sounds filled the air when massive storms, unbroken by oceanic barriers, swept across thousands of miles of uninterrupted land? The traces of this ancient world lie all around us, hidden in plain sight. The coal deposits that power our cities are the compressed remains of Pangean forests. The mountain ranges that divide our continents are scars left by the supercontinent's violent breakup. Even the distribution of certain species across modern continents makes sense only when we remember that their ancestors once lived on a single, connected landmass. But Pangea is more than just a chapter in Earth's geological history. It represents something profound about the nature of our planet, the idea that what we consider permanent and unchanging is actually fluid and temporary. The very ground beneath our feet is in constant motion, driven by forces so vast and patient that human lifespans are like heartbeats in comparison. As we prepare to journey back to this lost world, we must shed our modern assumptions about what Earth should look like. We must imagine a planet where the rules of geography, weather, and biology operated under completely different parameters. This is not just a story about rocks and continents. It is a story about life finding ways to thrive in conditions so extreme they challenge our understanding of what is possible. The cliff beneath your feet begins to crumble, and you realize that even in this ancient world, change was the only constant. The very formation of Pangea was not a single event, but a slow-motion collision of continents that took millions of years to complete. And even as it reached its maximum extent, the forces that would tear it apart were already stirring deep beneath the surface. Hundreds of millions of years before that cliff existed, the world was a very different place. Earth's landmasses wandered the globe like nomadic islands, carried by currents of molten rock that flowed beneath the planet's thin crust. These were not the familiar shapes of today's continents, but alien fragments of land with names that sound like forgotten spells: Laurussia, Gondwana, Siberia, Kazakhstania. The story of Pangea's birth begins not with a bang, but with the slowest possible dance imaginable. Tectonic plates, massive slabs of rock floating on the planet's molten interior, crept toward each other at speeds measured in centimeters per year. A human fingernail grows faster than these ancient continents moved. Yet over geological time, this glacial pace becomes an unstoppable force. Around 335 million years ago, during a period geologists call the Carboniferous, the scattered pieces of Earth's puzzle began to fit together. Laurussia, a landmass that would one day fragment into North America and Northern Europe, drifted southward toward the massive southern continent of Gondwana. Between them lay the Rheic Ocean, a body of water whose name is now known only to specialists, but whose closure would reshape the entire planet. The collision was not violent in human terms. No thunderous crashes or sudden upheavals marked the moment when these landmasses touched. Instead, the process unfolded with the inexorable patience of geological time. Ocean floors buckled upward, forming mountain ranges that scraped the sky. The Appalachians, the Ural Mountains, and the ancient peaks of Western Europe are monuments to these primordial collisions, their worn summits testament to hundreds of millions of years of wind and weather. As Laurussia and Gondwana merged, they formed the western portion of what would become Pangea. But the supercontinent was not yet complete. Smaller fragments continued to drift inward like cosmic debris drawn to a gravitational center. The Siberian Craton, carrying the future heart of Russia, approached from the north. Kazakhstan and other Central Asian terrains added their bulk to the growing mass. The mechanism driving these collisions lay hidden beneath Earth's surface in the behavior of convection currents within the planet's mantle. Hot rock rose from the depths, cooled, and sank back down in vast circular motions that lasted tens of millions of years. These currents acted like slow-motion conveyor belts, carrying the continents along for the ride. When multiple currents converged, they created zones where land masses were inevitably drawn together. But continental collision is never a clean process. As these ancient lands pressed against each other, their edges crumpled like fabric pushed together on a table. Sedimentary rocks that had formed peacefully on ocean floors were suddenly thrust upward, twisted, and folded into complex mountain systems. Volcanic activity increased as subduction zones, places where oceanic crust dove beneath continental margins, became more numerous and active. The assembly of Pangea coincided with remarkable changes in Earth's climate and atmosphere. The gradual removal of ocean barriers began to alter global weather patterns in ways that would persist for millions of years. Ocean currents that had previously circulated freely around separate continents were now blocked or redirected. This had profound implications for how heat and moisture moved around the planet. Meanwhile, life itself was adapting to these changing conditions. The Carboniferous period earned its name from the vast coal deposits formed during this time, the compressed remains of enormous swamp forests that thrived in the warm, humid conditions that prevailed as the continents converged. These forests, dominated by giant tree ferns and early seed plants, created some of the richest ecosystems Earth had ever known. As the final pieces of Pangea locked into place around 250 million years ago, during the Permian period, Earth found itself with a geography unlike anything that had existed before or has existed since. Roughly C-shaped when viewed from above, the supercontinent stretched nearly from pole to pole, with only a large embayment, called the Tethys Sea, breaking its eastern coastline. This was no accident of cosmic chance, but the result of fundamental forces that continue to shape our planet today. The same processes that created Pangea are still at work, slowly rearranging Earth's surface in ways that will create new supercontinents in the distant future. In a sense, the story of Pangea's formation is also the story of how our planet continuously recreates itself, ensuring that the world our descendants inherit will be as alien to them as Pangea is to us. The birth of the supercontinent was complete, but its story was just beginning. For the next 50 million years, Pangea would dominate the planet's surface, creating conditions for life that were both extraordinary and extreme. Even as Pangea reached its greatest extent, the forces of its destruction were already stirring. Deep beneath the supercontinent's heart, the same mantle convection that had drawn the continents together now began to pull them apart. What had been creation was becoming dissolution, but with the same geological patience that had characterized the supercontinent's birth. The breakup began subtly around 200 million years ago with a phenomenon geologists call rifting. Picture the Earth's crust as a massive sheet of ice on a warming lake. As temperatures rise, cracks begin to appear, spreading slowly at first, then widening into gaps that eventually become channels of open water. In Pangea's case, the warming came from below, as hot mantle material rose toward the surface, creating zones of weakness where the continent would eventually tear apart. The first major rift appeared along what would one day become the Atlantic Ocean, a line of volcanic activity stretched from what is now eastern North America to western Africa, marking the place where the supercontinent would split. But this was not a clean break. The process unfolded over millions of years, with periods of intense activity separated by long intervals of apparent calm. Imagine standing in the Pangean interior during one of these early rifting episodes. The ground beneath your feet would shudder with earthquakes that dwarf anything recorded in human history. Massive fissures would open in the earth, some stretching for hundreds of miles and gaping wide enough to swallow mountains. From these wounds in the planet's surface, molten rock would pour forth in quantities that beggar the imagination. These were not the modest volcanic eruptions we see today, but flood basalt's oceanic outpourings of lava that could cover areas the size of entire countries. The Central Atlantic Magmatic Province, formed during Pangea's initial breakup, covered more than 11 million square kilometers with layers of volcanic rock. The heat and toxic gases released by such eruptions may have triggered one of the most severe extinction events in Earth's history. As the rifts widened, seawater began to penetrate the growing gaps between the continents. At first, these were narrow, enclosed basins, hot, salty, and hostile to most forms of life. But gradually, as the seafloor spreading continued, these proto-oceans connected with the global ocean system, allowing currents to flow and life to flourish in the new marine environments. The breakup was not uniform. Some parts of Pangea separated quickly, geologically speaking, while others remained stubbornly connected for millions of additional years. The southern portion of the supercontinent, formed primarily from the ancient continent of Gondwana, began to fragment into the pieces we now recognize as South America, Africa, Antarctica, Australia, and India. But these separations occurred at different times and rates, creating a complex sequence of continental divorces. India's journey is perhaps the most dramatic example of this process. Originally nestled between Africa and Antarctica, in the heart of Gondwana, the Indian subcontinent broke free around 140 million years ago and began a remarkable voyage northward across the growing Indian Ocean. Moving at speeds of up to 20 centimeters per year, extraordinary by geological standards, India raced toward Asia like a geological missile. The collision between India and Asia, which began around 50 million years ago and continues today, created the Himalayan mountain range and the Tibetan Plateau. This ongoing collision has produced some of the most spectacular mountain scenery on Earth, but it also represents one of the final chapters in Pangea's dissolution, a process that transformed a unified supercontinent into the familiar continental configuration we know today. But the violence of Pangea's breakup extended far beyond earthquakes and volcanic eruptions. As the continents separated, they carried with them the fossil record of life that had evolved on the unified landmass. Species that had once been able to migrate freely across the supercontinent suddenly found themselves isolated on separate continents, leading to divergent evolutionary paths. The breakup also had profound effects on global climate. As new ocean basins opened and continental positions changed, ocean and atmospheric circulation patterns were completely reorganized. The formation of the Atlantic Ocean, for instance, eventually allowed the Gulf Stream to develop, fundamentally altering the climate of Western Europe. Similarly, the separation of Antarctica from other continents allowed the formation of the Antarctic Circumpolar Current, which helped lock the southern continent in its current deep freeze. Even today, 200 million years after it began, Pangea's dissolution continues. The Atlantic Ocean grows wider by several centimeters each year as North America and Europe drift apart. The Red Sea represents a modern rift valley that may one day become a full ocean, splitting Africa along its eastern edge. These processes remind us that Pangea's story is not ancient history, but part of an ongoing cycle of continental assembly and dispersal that will continue for billions of years to come. Meanwhile, new supercontinents are already in the planning stages of geological time. Computer models suggest that in 200 to 300 million years, the current continents may reassemble into new configurations with names like Pangea Ultima or Amasya. The shattering of Pangea was not an ending, but a transition one chapter in Earth's endless book of continental wandering. Beyond the shores of Pangea stretched an ocean so vast it defied comprehension. Panthalassa, the all-ocean, wrapped around the supercontinent like a liquid embrace that covered roughly 70% of Earth's surface. This was not merely a large sea, but a body of water so immense that sailing from Pangea's eastern shore to its western shore would have required crossing more than 20,000 kilometers of open ocean. Unlike the familiar oceans of today, divided and constrained by continents, Panthalassa formed an unbroken expanse of water that connected every latitude and longitude on the planet. Currents flowed freely across this aquatic realm, carrying heat, nutrients, and life forms in patterns that would be impossible in our modern, compartmentalized world. The sheer scale of Panthalassa created weather systems and oceanic phenomena that have no modern equivalent. Imagine the storms that could develop across such an unlimited fetch of water. With no continental barriers to break their momentum, typhoons and hurricanes could grow to continental proportions, their spiral arms stretching across distances that would span from New York to London. These megastorms would have carried enormous amounts of energy, capable of generating waves that could reach heights measured in hundreds of feet rather than mere tens of feet. The chemistry of Panthalassa was markedly different from modern oceans. During much of Pangea's existence, global sea levels were lower than today, and the ocean's composition reflected different atmospheric conditions. Oxygen levels in the deep ocean fluctuated dramatically, sometimes creating vast dead zones where life could not survive, and at other times supporting ecosystems of unusual richness and diversity. In the depths of Panthalassa, life took forms that seem almost alien to our modern understanding. Giant marine reptiles, ichthyosaurs, the size of modern whales, long-necked plesiosaurs, and armored placodonts ruled the open ocean. These were not merely larger versions of contemporary marine life, but creatures adapted to the unique conditions of a truly global ocean system. The absence of continental barriers also meant that oceanic circulation patterns operated on a planetary scale. Massive gyres, circular currents thousands of kilometers in diameter, moved water and nutrients around the globe in ways that profoundly influenced both marine ecosystems and global climate. Some computer models suggest that these supergyres could have transported warm water from equatorial regions to the poles with greater efficiency than modern ocean systems, creating more uniform global temperatures. But Panthalassa was not uniform across its vast expanse. Different regions developed distinct characteristics based on their latitude, depth, and relationship to Pangea's coastlines. The shallow seas that bordered the supercontinent environments geologists call epicontinental seas harbored rich ecosystems of corals, crinoids, and early fish. These marginal seas were like vast nurseries where new species evolved before spreading into the deeper ocean. The Tethys Sea, a large embayment that indented Pangea's eastern coast, played a particularly important role in marine evolution. This proto-Mediterranean served as a bridge between the northern and southern portions of Panthalassa, allowing species to migrate between different oceanic provinces. Many of the marine fossils found in rocks from this period show evidence of cosmopolitan distribution species that lived across multiple ocean basins, made possible by the connected nature of Panthalassa. Seasonal changes in Panthalassa would have been extreme beyond modern comprehension. Without land masses to moderate temperature swings, vast regions of the ocean could have experienced dramatic heating and cooling cycles. During summer months in each hemisphere, enormous areas of surface water would have heated to temperatures that might have been lethal to many modern marine species. Conversely, winter cooling could have created temporary ice sheets that covered millions of square kilometers of ocean surface. The relationship between Panthalassa and Pangea's climate was intimate and complex. The ocean served as both a heat reservoir and a moisture source for the supercontinent's weather systems. Monsoon patterns of extraordinary intensity could have developed as seasonal temperature differences between the vast ocean and the equally vast landmass created pressure gradients unlike anything in our modern world. Deep in Panthalassa's abyssal depths, hydrothermal vents released mineral-rich water that supported unique ecosystems. These underwater oases were likely more important during Pangea's time than they are today, as the increased volcanic activity associated with continental rifting would have created more numerous and active vent systems. Some scientists speculate that these deep-sea environments may have served as refugia during mass extinction events, preserving lineages that later recolonized shallower waters. As Pangea began to break apart, Panthalassa's days were numbered. The opening of new ocean basins gradually divided the superocean into the Pacific, Atlantic, and Indian Oceans we know today, but the transition was not immediate. For millions of years, seaways connected these nascent oceans, maintaining some of Panthalassa's global circulation patterns even as its unity was being destroyed. The legacy of Panthalassa lives on in the Pacific Ocean, which represents the largest remaining portion of the ancient superocean. When we look out across the Pacific's vast expanse, we re-seeing the closest thing our modern world offers to the oceanic realm that once dominated our planet. Yet even the Pacific, constrained by the Ring of Fire and divided by island chains, is but a shadow of the limitless ocean that once surrounded Pangea. Venture inland from Pangea's coastal regions, and you would have entered one of the most forbidding landscapes Earth has ever produced. The supercontinent's interior was a realm of extremes, vast deserts that stretched for thousands of kilometers without interruption, creating conditions so harsh that they challenged the very limits of life's adaptability. These were not the romantic sand dune deserts of our imagination, but something far more alien and unforgiving. Picture endless expanses of red sandstone and sun-baked mudstone, broken only by the occasional dry riverbed that might see water once in a decade. The scale of these desert regions dwarfed anything that exists today. Imagine the Sahara Desert multiplied several times over and extending, unbroken from what would one day be eastern Canada to western China. The formation of Pangea's interior deserts resulted from a combination of factors that created perfect conditions for aridity. As moisture-laden air from Panthalassa moved inland, it was forced to release its water content long before reaching the continent's heart. By the time winds penetrated more than a few hundred kilometers from the coast, they carried virtually no moisture, creating a rain shadow effect on a continental scale. The sheer distance from any major water body meant that the interior of Pangea experienced extreme temperature fluctuations unknown in our modern world. During the day, surface temperatures could have soared beyond 60 degrees Celsius in some regions, hot enough to kill most modern plant and animal species within hours. At night, with no atmospheric moisture to trap heat, temperatures could plummet by 40 or 50 degrees, creating thermal stress that would have shattered rocks and challenged any organism attempting to survive in such conditions. Wind was a dominant force in these interior wastelands. With no mountain ranges or forests to break their momentum, winds could build up tremendous energy as they swept across thousands of kilometers of flat terrain. Dust storms of unimaginable proportions would have been common walls of sand and debris that could stretch from horizon to horizon, blocking out the sun for days at a time and scouring the landscape with erosive power that carved strange formations in the bedrock. Yet life, in its remarkable tenacity, found ways to exist even in these extremes. Fossil evidence suggests that specialized reptiles and early archosaurs, ancestors of dinosaurs and crocodiles, developed adaptations that allowed them to thrive where few other organisms could survive. These creatures evolved sophisticated ways of conserving water, regulating body temperature, and finding shelter from the relentless sun and wind. Some of the most extraordinary adaptations involved burrowing. Extensive fossil burrow systems from this period reveal complex underground networks that could extend for meters below the surface. These subterranean refuges provided escape from both the scorching heat of day and the bitter cold of night, creating microenvironments where temperatures remained relatively stable. Plant life in Pangea's interior faced equally extreme challenges. The few species that managed to colonize these regions developed revolutionary survival strategies. Some evolved thick, waxy coatings that could withstand both extreme heat and desiccation. Others developed extensive root systems that could tap into groundwater sources many meters below the surface, or specialized structures that could extract moisture from the rare dew that formed during the brief periods when temperatures dropped below the dew point. The rock formations created during this period tell their own story of extreme conditions. Massive deposits of red sandstone and mudstone preserve evidence of flash flood, events that could transform the landscape in a matter of hours. When rare rainstorms did occur, they unleashed torrents of water that carved temporary rivers through the desert, depositing layers of sediment that would eventually become some of the most distinctive geological formations on Earth. Seasonal variations in these interior deserts were extreme beyond modern comprehension. During certain periods of the year, the convergence of atmospheric pressure systems could have created brief windows when moisture actually penetrated to the continental interior. These rare events might have triggered explosive blooms of life plants that had remained dormant for years, suddenly sprouting, growing, reproducing, and dying within a matter of weeks. The mineral wealth of these ancient desert regions was extraordinary. The extreme chemical weathering processes operating under such conditions concentrated metals and minerals in ways that created deposits of copper, uranium, and other valuable elements. Some of the world's major mineral deposits can be traced back to processes that operated in Pangea's interior deserts, making these seemingly barren landscapes economically important even today. Perhaps most remarkably, evidence suggests that even these extreme environments played a role in the evolution of life. The harsh selective pressures of Pangea's interior may have driven the evolution of many of the physiological innovations that would later allow life to colonize terrestrial environments more successfully. Adaptations that first evolved to survive in these superdeserts would prove invaluable as climate conditions changed and new habitats became available. As Pangea began to break apart and ocean basins opened, the extreme interior deserts gradually gave way to more moderate climates. But for millions of years, these vast wastelands were among Earth's most prominent features, landscapes so extreme they seemed almost extraterrestrial, yet playing a crucial role in shaping the evolution of life on our planet. The legacy of these ancient deserts can still be seen today in the red sandstone formations of the American Southwest, the desert landscapes of Central Australia, and the arid regions of Inner Asia, all fragments of Pangea's heart, scattered across the modern world, but still bearing witness to one of the most extreme environments Earth has ever produced. Along Pangea's coastal margins, where oceanic moisture could still penetrate inland, an entirely different world flourished. These were forests unlike anything that exists today, vast woodlands, dominated by primitive plants that had evolved under the unique conditions of the supercontinent's early formation. Here, in a narrow band between the harsh interior deserts and the endless ocean, life exploded in forms that seem almost mythical to our modern eyes. The trees that dominated these ancient forests were giants in every sense. Lepidodendron, the scale trees, could reach heights of 40 meters or more, their trunks marked with distinctive diamond-shaped scars where leaves had attached. These were not true trees in the modern sense, but massive club mosses that had evolved to exploit the warm, humid conditions along Pangea's edges. When they died and fell, their trunks created natural bridges and clearings that shaped the forest ecosystem for decades. Beneath the canopy of scale trees grew an understory that would have seemed alien to any modern observer. Giant tree ferns unfurled fronds the size of modern palm trees, creating dense tangles of vegetation that filtered the sunlight into a green, aquatic glow. Seed ferns, plants that were neither true ferns nor true seed plants, but something in between, added to the forest's otherworldly character with their enormous compound leaves that could span several meters from tip to tip. The air itself was different in these ancient forests. Oxygen levels during much of Pangea's existence were significantly higher than today, sometimes reaching concentrations of 35% compared to our modern 21%. This oxygen-rich atmosphere had profound effects on the forest ecosystem, allowing combustion to occur more readily and supporting metabolisms that would be impossible under current conditions. This high oxygen environment enabled the evolution of arthropods of extraordinary size. Dragonflies with wingspans approaching a meter patrolled the forest clearings, their compound eyes reflecting the filtered sunlight like living jewels. Millipedes longer than modern snakes crawled through the leaf litter, while cockroaches the size of small birds scuttled up the massive tree trunks. These creatures were not aberrations, but natural products of an atmosphere that could support much larger invertebrates than our modern world allows. The soundscape of these forests would have been unlike anything heard on Earth today. The lack of birds, which had not yet evolved, meant that the forests were filled instead with the sounds of insects, amphibians, and early reptiles. Giant dragonflies created a constant buzzing that could be heard from kilometers away. Early amphibians called from hidden pools with voices that could carry across the entire forest. A crash of falling scale trees, weakened by their own enormous size, provided a percussion that punctuated the forest's symphony at irregular intervals. Water played a crucial role in shaping these coastal ecosystems. Seasonal monsoons, intensified by the contrast between Pangea's hot interior and the cooler ocean, could dump enormous amounts of rainfall on the forests during certain periods of the year. This created a boom and bust cycle where forests would flood for months at a time, then experience extended dry periods that tested every species' survival strategies. The forest floors of these ancient woodlands were carpeted with organic matter in quantities that boggle the modern imagination. Without significant populations of wood-decomposing fungi, which had not yet evolved, their modern efficiency dead plant material accumulated in layers that could reach many meters in thickness. These organic deposits would eventually become the coal seams that power much of our modern industrial civilization, representing stored sunlight from forests that died out hundreds of millions of years ago. Evolution proceeded at a rapid pace in these forest environments. The combination of high oxygen levels, abundant plant life, and relatively stable climate conditions created opportunities for new species to emerge and diversify quickly. Early reptiles began to explore ecological niches that had previously been dominated by amphibians, developing more efficient respiratory systems and reproductive strategies that would eventually allow them to colonize drier environments. The relationship between plants and animals in these forests was fundamentally different from modern ecosystems. Without flowering plants, there were no complex pollination relationships between insects and flowers. Instead, most plants relied on wind pollination or simple spore dispersal mechanisms. This meant that the intricate co-evolutionary relationships we see in modern forests had not yet developed, creating ecosystems that operated according to very different rules. As seasons changed, these forests underwent transformations that were both subtle and dramatic. During wet periods, the forests could expand rapidly inland, with fast-growing plants colonizing areas that had been too dry to support vegetation during drier seasons. Conversely, during dry periods, entire sections of forest could die back, leaving behind extensive deposits of organic matter that would contribute to coal formation. The eventual decline of these ancient forests was tied to the changing climate conditions that accompanied Pangea as later history. As the supercontinent's interior became increasingly arid and global climate patterns shifted, the narrow band where these forests could thrive began to shrink. Many of the giant plants that had dominated these ecosystems were unable to adapt to changing conditions and gradually went extinct, leaving only fossil traces of their former glory. Yet the legacy of these ancient forests extends far beyond their fossil remains. The evolutionary innovations that developed in these oxygen-rich woodlands, more efficient respiratory systems, better water conservation strategies, and improved reproductive mechanisms would prove crucial for life's eventual colonization of Earth's drier environments. In a very real sense, these forests at the edge of time served as evolutionary laboratories where life developed many of the adaptations that would allow it to thrive in the post-Pangean world. In a world without oceanic barriers, life could spread across Pangea like ink spreading through water. This unprecedented continental unity created evolutionary opportunities that would never exist again in Earth's history. Species that evolved in one corner of the supercontinent could migrate thousands of kilometers to colonize new environments, leading to a remarkable homogenization of life across vast distances. The reptiles of Pangea were pioneers in the truest sense, representing life's first serious attempt to fully colonize terrestrial environments. These were not the small lizards and snakes we associate with modern reptiles, but magnificent creatures that ranged from dog-sized early dinosaurs to massive herbivores that approached the size of modern elephants. Their success lay in revolutionary adaptations that allowed them to break free from the water-dependent life cycle that had constrained their amphibian ancestors. Dimetrodon, with its distinctive sail-like back fin, roamed the earlier forests and semi-arid regions of Pangea like a living solar panel. This remarkable predator, often mistaken for a dinosaur, but actually more closely related to mammals, used its enormous dorsal sail to regulate body temperature, catching morning sunlight to warm up quickly and using blood flow to dump excess heat during the scorching afternoons. Standing nearly 4 meters long, Dimetrodon was one of the first large terrestrial predators to achieve truly efficient thermoregulation. The herbivores of Pangea developed equally impressive adaptations for processing the tough, fibrous plant material that dominated the supercontinent's vegetation. Massive parasaurs, looking like reptilian tanks covered in bony studs and spikes, could weigh as much as modern rhinoceros. Their powerful jaws and specialized teeth allowed them to process enormous quantities of primitive plant material, filling ecological niches that would later be occupied by mammalian megaherbivores. Perhaps most remarkably, Pangea's unified geography allowed for the evolution of truly cosmopolitan species organisms that could be found across multiple continents during a time when those continents were joined. Fossil evidence shows that certain species of early archosaurs, the ancestors of dinosaurs and crocodiles, had ranges that spanned from what is now eastern North America to western China. This level of geographic distribution would be impossible in our modern ocean-divided world. The amphibians of Pangea included some of the most spectacular creatures that have ever lived. Eriops, a massive amphibian predator reaching lengths of 2 meters, lurked in the warm pools and rivers that dotted the supercontinent's landscape. With a skull nearly half a meter long and jaws filled with sharp teeth, Eriops was perfectly adapted for capturing fish and smaller tetrapods in the oxygen-rich waters of the Carboniferous period. But it was in the realm of early archosaurs that Pangea truly showcased life's innovative potential. These animals, ancestors to both dinosaurs and crocodilians, began experimenting with body plans and lifestyles that would eventually lead to some of the most successful vertebrate groups in Earth's history. Early forms like Euparkeria demonstrated the basic archosaur body plan erect limbs, improved respiratory systems, and more sophisticated behavioral capabilities than their theropsid contemporaries. The absence of geographical barriers also facilitated the rapid spread of evolutionary innovations across Pangea. New adaptations that appeared in one part of the supercontinent could quickly spread to populations thousands of kilometers away, accelerating the pace of evolutionary change. This connectivity may have contributed to the relatively rapid transitions between different evolutionary faunas that characterized Pangea's history. Marine reptiles, though technically living in Panthalassa rather than on Pangea itself, were equally spectacular. Early ichthyosaurs began their transition from terrestrial to fully aquatic lifestyles during this period, developing streamlined body shapes and specialized sensory systems that would eventually allow them to become the ocean's top predators. These marine pioneers showed that reptilian innovations were not limited to terrestrial environments, but could unlock new ecological opportunities in any habitat. The synapsids, the group that would eventually give rise to mammals, were reaching their evolutionary peak during Pangea's early history. Massive predators like Innostroncevia, with saber-tooth-like canines, dominated many terrestrial ecosystems. These creatures combined reptilian and proto-mammalian characteristics in ways that created entirely unique ecological roles. Their eventual decline and replacement by archosaurs represents one of the most significant evolutionary transitions in vertebrate history. Social behaviors among Pangean reptiles may have been more sophisticated than previously thought. Recent fossil evidence suggests that some species engaged in complex parental care, territorial behaviors, and possibly even primitive forms of communication. The stable, extensive habitats available on the unified supercontinent may have provided opportunities for the evolution of social complexity that would have been impossible in more fragmented landscapes. The extinction events that periodically swept across Pangea were particularly devastating precisely because of the continent's unified nature. When environmental changes occurred, they could affect enormous geographic areas simultaneously, leaving few refugia where species could survive. The end Permian extinction, which eliminated roughly 90% of all species, was able to achieve such thoroughness partly because Pangea's unity meant that environmental catastrophes could have truly global effects. As Pangea began to fragment, the evolutionary consequences were immediate and profound. Species that had enjoyed continent-spanning distributions suddenly found themselves divided by growing ocean basins. This geographic isolation led to rapid speciation as separated populations adapted to their new, more limited environments. In a sense, the breakup of Pangea created the biogeographic diversity that characterizes our modern world, ending forever the era when a single species could walk from pole to pole across unbroken land.
Step into the oxygen-saturated forests of early Pangea, and you would encounter insects that defy modern comprehension. This was a world where dragonflies ruled the skies with wingspans approaching those of modern eagles. where millipedes stretched longer than contemporary automobiles, and where cockroaches scuttled through the undergrowth with the mass and presence of small mammals. The secret to these giants lay in the very air they breathed during the Carboniferous period. Atmospheric oxygen levels reached concentrations of 35%, nearly twice what we experience today. For insects, which rely on passive diffusion to transport oxygen through their bodies via a network of tubes called trachea, this oxygen-rich environment removed the size constraints that limit modern arthropods. The more oxygen available, the larger an insect could grow while still maintaining adequate oxygen delivery to all its tissues. Meganeura, the most famous of the giant dragonflies, patrolled the skies of Pangea with wings that could span 75 centimeters from tip to tip. These aerial predators were not merely scaled-up versions of modern dragonflies, but represented an entirely different approach to flight and predation. Their massive size allowed them to hunt prey that would be impossible targets for modern insects, small tetrapods, large amphibians, and even other flying insects that would dwarf any contemporary aerial arthropod. The hunting strategies of these giant dragonflies were likely as impressive as their size. Computer models suggest that Meganeura could achieve flight speeds of up to 70 kilometers per hour, fast enough to outmaneuver many of the primitive flying reptiles that were just beginning to experiment with powered flight. Their compound eyes, enlarged proportionally with their bodies, could probably detect movement and track prey with a precision that made them the apex aerial predators of their time. On the forest floor, Arthropleura represented perhaps the most extreme example of arthropod gigantism. These millipede-like creatures could reach lengths exceeding 2.5 meters and weights of perhaps 50 kilograms or more. Despite their fearsome size, Arthropleura were herbivores, using their powerful mandibles to process the abundant plant material that carpeted Pangea's forest floors. Their segmented bodies, protected by tough, chitinous exoskeletons, made them virtually impervious to the predators of their era. The ecological impact of these giant arthropods extended far beyond their immediate predator-prey relationships. Arthropleura, as they moved through the forests, served as living bulldozers, creating pathways through dense vegetation and churning organic matter into the soil in ways that affected entire forest ecosystems. Their feeding activities helped break down plant material and accelerate the formation of the organic deposits that would eventually become coal seams. Giant cockroaches of the genus Atheroblottia reached lengths of up to 50 centimeters, making them roughly the size of modern house cats. These creatures filled ecological niches that didn't exist before or since, serving as major detritivores that could process enormous quantities of decaying organic matter. Their size allowed them to exploit food sources that would have been impossible for smaller insects to utilize effectively. The respiratory systems of these giant insects were marvels of biological engineering. To move oxygen efficiently through bodies of unprecedented size, They evolved highly branched tracheal networks that maximized surface area for gas exchange. Some species may have even developed primitive air sacs inflatable chambers that could store oxygen and improve breathing efficiency during periods of high activity. Flight in the giant insects of Pangea operated according to aerodynamic principles that have no modern equivalent. The combination of high atmospheric oxygen and different air density created conditions where insects could achieve lift and maneuverability that would be impossible today. Some researchers suggest that the giant dragonflies may have been capable of brief periods of gliding flight, using thermal updrafts to soar above the forest canopy like miniature condors. The diversity of giant insects during this period was extraordinary. Beyond the famous dragonflies and millipedes, Pangea was home to enormous mayflies, giant beetles, and prehistoric relatives of modern stick insects that could exceed a meter in length. Each group exploited different aspects of the high oxygen environment, creating an arthropod fauna that was both more diverse and more ecologically dominant than anything seen before or since. The social behaviors of some giant insects may have been remarkably complex. Fossil evidence suggests that some species formed aggregations or colonies, possibly for protection, reproduction, or resource exploitation. The increased neural capacity made possible by larger body sizes may have allowed for more sophisticated behaviors than we typically associate with modern insects. The decline of giant insects was not sudden, but gradual, tied to the slowly decreasing oxygen levels that characterized the later Permian period. As atmospheric oxygen dropped toward modern levels, the physiological constraints that had been lifted during the Carboniferous began to reassert themselves. Species that had evolved in the high oxygen environment found themselves unable to maintain adequate oxygen delivery to their oversized bodies. Climate change also played a role in the giant's demise. As Pangea's climate became more arid and seasonal variations became more extreme, the stable, humid conditions that had supported the massive arthropod fauna began to disappear. Many species were unable to adapt to the new environmental conditions, particularly those that had become highly specialized for life in the oxygen-rich forests. The legacy of Pangea's giant insects lives on in the fossil record and in our understanding of how atmospheric conditions can shape the evolution of life. These creatures represent one of the most dramatic examples of how changes in Earth's atmospheric chemistry can create evolutionary opportunities that seem almost fantastical from our modern perspective. They remind us that the insects we see today, impressive as they are, represent only a fraction of arthropod potential when environmental conditions permit truly gigantic forms to evolve.
Across the vast expanse of Pangea, weather systems developed that dwarf anything our modern world has ever experienced. With no oceanic barriers to interrupt their development and continental distances that stretched for thousands of uninterrupted kilometers, atmospheric disturbances could grow to proportions that seem almost mythological in scale. Picture a thunderstorm system that could span the distance from New York to Moscow. its towering cumulonimbus clouds reaching heights that scraped the very edge of space. This was not merely possible in Pangea's world, it was inevitable. The massive temperature differentials between the supercontinents, scorching interior deserts, and the moderating influence of Panthalassa created pressure gradients that drove weather systems of unprecedented magnitude. The monsoon systems that developed along Pangea's margins were particularly spectacular. As seasonal temperature differences between the vast landmass and the equally vast ocean created massive pressure differentials, winds could build to velocities that have no modern parallel. These were not the relatively modest monsoons of contemporary South Asia, but atmospheric rivers that could carry moisture from oceanic source regions thousands of kilometers inland, dumping precipitation in quantities that could reshape entire landscapes in a matter of days. Lightning during these superstorms would have been a constant, terrifying presence. With no tall vegetation or structures to attract strikes, electrical discharges could arc horizontally for dozens of kilometers, creating curtains of fire that swept across the landscape. The electromagnetic effects of such massive electrical activity may have been powerful enough to interfere with the navigation systems of migrating animals, forcing evolutionary adaptations we can barely imagine. Tornadoes on Pangea could achieve dimensions that make modern twisters seem like dust devils by comparison. With thousands of kilometers of flat terrain over which to develop and intensify, rotating storm systems could maintain their structure and continue growing for days or even weeks. Some atmospheric models suggest that supercell thunderstorms could have produced tornado families with individual vortices reaching widths of several kilometers, spinning columns of air, powerful enough to scour bedrock and move massive boulders across vast distances. The dust storms that swept across Pangea's interior deserts were phenomena of almost planetary scale. With no vegetation or topographic barriers to impede their development, wind-driven haboobs could build walls of sand and debris that stretched from horizon to horizon, reaching heights of 10 kilometers or more. These atmospheric tsunamis could transport material across continental distances, redistributing sediments on a scale that permanently altered the landscape. Hailstorms in Pangea's climate could produce ice stones of extraordinary size. The powerful updrafts in the supercontinent's massive thunderstorm systems could keep hailstones aloft long, enough for them to grow to sizes approaching those of modern bowling balls. When these ice missiles finally fell to Earth, they would have created impact craters and delivered enough kinetic energy to shatter rocks and devastate any vegetation unfortunate enough to lie in their path. The seasonal variations in Pangea's weather were extreme beyond modern comprehension. During summer months, the continental interior could heat to temperatures that would be lethal to most modern life forms, creating thermal low-pressure systems that drew moisture-laden air inland with tremendous force. Conversely, winter cooling could create high-pressure systems of continental proportions, generating outflow winds that could maintain hurricane-force velocities for thousands of kilometers. Atmospheric rivers corridors of concentrated water vapor transport could stretch, unbroken from Panthalassa's tropical regions to Pangea's polar margins. These aerial rivers carried more water than the Amazon River system, creating precipitation events that could deliver meters of rainfall over periods of just a few days. The erosive power of such deluges carved canyons and river systems on scales that dwarf even the Grand Canyon. The acoustic effects of Pangean weather would have been as extraordinary as the visual spectacle. Thunder from the massive storm systems could create infrasound, wave sound frequencies below the range of human hearing that could travel for thousands of kilometers through the atmosphere and solid Earth. These acoustic signals may have served as long-distance communication systems for Pangea's wildlife, allowing animals to sense weather changes days or even weeks in advance. Flash flooding on Pangea reached scales that transformed entire regions in matters of hours. When massive storm systems stalled over the supercontinent's drainage basins, They could deliver rainfall measured in meters rather than centimeters. Rivers that normally carried modest flows could become raging torrents hundreds of kilometers wide, capable of transporting boulders the size of modern houses and carving new channels across previously stable landscapes. The interaction between Pangea's weather systems and its unique geography created feedback loops that amplified meteorological extremes. Dark surfaces in the interior deserts absorbed solar radiation with tremendous efficiency, creating thermal hotspots that could drive convection to extraordinary heights. These ascending air masses could trigger storm systems visible from space, with cloud tops reaching altitudes where ice crystals formed in patterns that have no modern equivalent. Pressure systems on Pangea could achieve intensities that would register off the scale of modern meteorological instruments. High-pressure systems over the continental interior could create barometric readings that would be considered impossible under current atmospheric conditions. Similarly, the low-pressure systems associated with major storm complexes could create partial vacuums that would affect everything from animal physiology to the boiling point of water. The gradual breakup of Pangea brought these extreme weather systems to an end, as the formation of new ocean basins and the division of the supercontinent created the more moderate, compartmentalized weather patterns we experience today. But for millions of years, Pangea's atmosphere was dominated by meteorological phenomena that were as much a part of its alien character as its strange plants and giant insects. Weather systems so extreme, they helped shape the evolution of life itself. In the deepest layers of human memory, embedded in myths and legends that predate written history, there may lie echoes of truths so ancient they stretch back to times when our planet wore an entirely different face. Could the flood stories that appear in cultures across the globe, from Noah's deluge to the Sanskrit accounts of Pangea, from Aboriginal Dreamtime floods to Native American emergence tales, preserve some genetic memory of the catastrophic changes that accompanied Pangea's destruction? The timing seems almost impossibly distant. The final breakup of Pangea occurred roughly 200 million years ago, while the earliest human ancestors appeared only a few million years ago. Yet some researchers propose that certain geological catastrophes may have been so profound that they left marks, not just in stone, but in the collective unconscious of life itself, traces that survived through countless generations of evolutionary change to resurface in the mythologies of conscious beings who would never know their ultimate origin. Consider the remarkable consistency of flood myths across human cultures that had no contact with each other. The Mesopotamian epic of Gilgamesh describes a deluge that covered the entire world, while the Aztec legend of the fifth sun tells of a universal flood that destroyed a previous world. Hindu texts speak of cosmic cycles ending in universal inundation, and Aboriginal Australian stories describe the flooding of entire continents. These stories, emerging from isolated cultures across the globe, share structural elements that suggest either a common source or a shared experience encoded in ways we don't yet understand. The geological record of Pangea's breakup does indeed include catastrophic flooding events on scales that beggar the imagination. As rifts opened in the supercontinent's crust, massive amounts of seawater poured into previously dry basins, creating inland seas that could inundate areas the size of entire modern countries within geological eye blinks. The formation of the Atlantic Ocean, for instance, involved the progressive flooding of rift valleys that had been dry land for millions of years. But perhaps more intriguing are the stories that speak of lands where one could walk around the entire world without crossing water, a remarkably accurate description of life on Pangea. Aboriginal Australian mythology includes accounts of a time when all lands were connected, when one could travel from any place to any other place without needing to cross the sea. Similar themes appear in the cosmologies of cultures as diverse as the Hopi of North America and the indigenous peoples of Siberia. The myth of Atlantis, as recorded by Plato, describes an advanced civilization on a landmass it was eventually swallowed by the ocean. While most scholars interpret this as either allegory or fiction, some fringe theorists wonder whether Atlantis might represent a folk memory of continents that literally did disappear beneath the waves as Pangea fragmented. The description of Atlantis as existing beyond the Pillars of Hercules, beyond the known world, could metaphorically describe landmasses that existed before the Atlantic Ocean opened. Volcanic catastrophes, which played a major role in Pangea's destruction, also feature prominently in global mythologies. Stories of fire raining from the sky, of mountains exploding with world-ending violence, and of the earth itself splitting open appear in traditions ranging from Norse Ragnarok to Polynesian creation myths. The massive volcanic episodes that accompanied continental rifting events, like the formation of the Central Atlantic Magmatic Province, were indeed catastrophes of mythological proportions. Even more speculative is the possibility that some geological features of Pangea itself influenced the development of mythological themes. The supercontinent's vast interior deserts, with their extreme conditions and otherworldly landscapes, may have served as the template for mythological underworlds and lands of the dead that appear in cultures worldwide. The harsh, lifeless character of these regions could explain why so many cultures developed concepts of barren, afterlife realms located in the interior of the Earth. The cyclical nature of continental assembly and dispersal, the Wilson cycle that governs the opening and closing of ocean basins, bears remarkable similarity to the cyclical cosmologies found in many ancient cultures. Hindu concepts of cosmic cycles lasting hundreds of millions of years, during which universes are created, destroyed, and recreated, mirror with startling accuracy the actual timescales over which supercontinents form and break apart. Some researchers have proposed that the genetic basis of instinctive behaviors might preserve information across evolutionary timescales that exceed individual species' lifespans. If certain environmental responses became so fundamental to survival that they were encoded at the genetic level, then catastrophic changes in Earth's configuration might have left marks in the behavioral repertoires of entire lineages. The universal human fear of being trapped in enclosed spaces, for instance, might trace back to ancestors who survived previous geological catastrophes by seeking open ground. The orientation behaviors of migrating animals provide another potential link between deep geological history and inherited memory. Many species navigate using magnetic field references that are calibrated to current continental positions. But some migration routes seem to follow patterns that would have made more sense when continents were arranged differently. Could these behaviors preserve geographic information from times when Pangea was still intact? Archaeological mysteries also contribute to this speculative picture. Massive stone structures found in various parts of the world sometimes incorporate astronomical alignments and geological knowledge that seems to exceed what should have been possible for their builders. While conventional explanations focus on the sophistication of ancient civilizations, some researchers wonder whether these monuments might incorporate much older knowledge information that had been passed down through countless generations from times when continental arrangements were fundamentally different. The emergence of plate tectonics theory in the 20th century provided scientific validation for ideas that had existed in various forms for centuries. Long before continental drift was accepted by mainstream geology, cultures around the world had stories suggesting that lands had once been connected differently, or that the configuration of continents had changed over time. This prescient understanding, preserved in oral traditions, suggests that human intuition about geological processes may be more sophisticated than we typically assume. Whether these mythological parallels represent genuine folk memories, psychological archetypes, or mere coincidence remains an open question. But the possibility that our deepest cultural stories might preserve traces of Earth's most profound transformations adds another layer of mystery to the already remarkable story of Pangea, suggesting that the supercontinent's influence on life may extend far beyond the geological and biological realms. into the very foundations of human consciousness and culture. Beneath Pangea's surface, forces of unimaginable power stirred restlessly, seeking release through the planet's thin crust. The supercontinent was not a stable, permanent feature, but a temporary arrangement of crustal fragments balanced precariously above a churning mantle that moved, according to its own deep rhythms. When these subterranean forces finally found expression, they did so with a violence that could reshape entire regions and alter the course of evolution itself. The volcanic activity associated with Pangea was not the familiar, localized eruptions we see in our modern world, but something far more catastrophic: flood basalts that could cover areas larger than entire countries with molten rock. The Siberian traps, formed during the end Permian period, as Pangea neared its maximum extent, represent perhaps the most extreme volcanic event in Earth's recorded history. For nearly 1 million years, this region poured forth lava in quantities that boggle the imagination, creating a volcanic province covering more than 2 million square kilometers. Picture standing at the edge of one of these eruption zones during its active phase. The ground beneath your feet would shake continuously with earthquakes that never ceased, as magma chambers the size of mountain ranges emptied their contents onto the surface. Rivers of molten rock, some flowing at temperatures exceeding 1200 degrees Celsius, would stream across the landscape like liquid fire, consuming everything in their path and creating new topography that could remain glowing red-hot for months. After the initial eruption, the atmospheric effects of such massive volcanism were global in scope and devastating in their impact. Enormous quantities of sulfur dioxide, carbon dioxide, and other volcanic gases poured into the atmosphere, creating conditions that could trigger rapid climate change and mass extinction. The end Permian extinction event, which eliminated roughly 90% of all marine species and 70% of terrestrial vertebrates, coincided precisely with the peak activity of the Siberian Traps volcanism. But the Siberian Traps were not unique. As Pangea began to fragment, massive volcanic provinces erupted along the lines of weakness where the supercontinent would eventually split. The Central Atlantic Magmatic Province, formed as North America began to separate from Africa, covered parts of what are now 4 continents with layers of volcanic rock. These eruptions were so massive that they left their chemical signature in rocks around the world, creating a permanent record of one of the most violent periods in Earth's history. The mechanisms driving this extreme volcanism lay deep within the Earth's mantle, where enormous plumes of hot rock rose from near the core mantle boundary. These mantle plumes, sometimes called superplumes, could carry heat and material from depths of nearly 3,000 kilometers to just beneath the Earth's surface. When these hot plumes encountered the relatively thin continental crust of Pangea, they created zones of intense volcanic activity that could persist for millions of years. The immediate effects of major volcanic episodes were catastrophic beyond modern comprehension. Pyroclastic flows, avalanches of superheated gas and volcanic debris could travel at speeds exceeding 700 kilometers per hour, incinerating everything within hundreds of kilometers of eruption sites. Volcanic ash clouds rose to heights of 50 kilometers or more, blocking sunlight across entire continents and creating artificial winters that could last for years. The longer-term effects were equally dramatic. Massive injections of carbon dioxide into the atmosphere created greenhouse conditions that raised global temperatures by 10 degrees Celsius or more. Ocean chemistry changed dramatically as volcanic emissions acidified seawater and depleted oxygen levels. These changes created cascading effects throughout Earth's ecosystems, triggering extinction events that reset the course of evolutionary history. Yet volcanism also played a creative role in Pangea's story. Volcanic soils, enriched with minerals from the Earth's deep interior, created some of the most fertile growing conditions the planet had ever seen. As volcanic activity waned, these nutrient-rich substrates supported explosive diversification of plant and animal life. The volcanic landscapes also created new habitats and ecological niches that drove evolutionary innovation. The formation of large igneous provinces during Pangea's history was not random, but followed predictable patterns related to mantle convection and continental configuration. Computer models suggest that the assembly of Pangea actually insulated the underlying mantle, trapping heat and creating conditions that made massive volcanic events more likely. This feedback relationship between continental configuration and volcanic activity may be a recurring theme in Earth as long-term evolution. Some of the most spectacular volcanic features from Pangea's time remain visible today, though weathered and eroded by hundreds of millions of years of exposure. The Palisades along the Hudson River, the dramatic cliffs of the Bay of Fundy, and the columnar basalt formations of Scotland's Inner Hebrides are all remnants of the Central Atlantic magmatic province. These ancient volcanic landscapes provide tangible connections to one of the most violent chapters in Earth's history. The minerals created by Pangean volcanism have had profound impacts on human civilization. Massive ore deposits of copper, nickel, platinum, and other valuable metals were concentrated by volcanic processes operating during the supercontinent's existence. The economic geology of entire regions can be traced back to volcanic events that occurred hundreds of millions of years ago, making Pangea's fiery legacy an integral part of our modern technological society. Perhaps most remarkably, some researchers propose that the extreme volcanic activity of Pangea's era may have played a crucial role in the evolution of complex life. The environmental stress created by repeated volcanic catastrophes may have accelerated evolutionary change, forcing life to develop new strategies for survival that ultimately increased biological diversity and complexity. In this view, the volcanic violence that repeatedly devastated Pangean ecosystems was also a creative force that pushed evolution toward ever greater sophistication. The gradual decline of Pangean volcanism as the supercontinent fragmented and mantle heat dissipated marked the end of one of the most geologically active periods in Earth's history. Our modern world, with its relatively modest volcanic activity confined to specific tectonic settings, represents a much quieter chapter in the planet's geological story. Yet the legacy of Pangea's volcanic violence remains written in the rocks beneath our feet, and the very composition of our atmosphere, a permanent reminder of the awesome forces that shaped our planet's early history.
In the aftermath of the Great Dying that marked the end of the Permian period, Pangea became a laboratory for gigantism unlike anything Earth had seen before or has seen since. As life slowly recovered from the most devastating extinction event in planetary history, the survivors found themselves in a world with vast ecological niches waiting to be filled. The response was extraordinary. Evolution began experimenting with body sizes that pushed the very limits of what land-dwelling animals could achieve. The archosaurs, that remarkable group of reptiles that would eventually give rise to dinosaurs, crocodiles, and birds, emerged as the primary architects of this age of giants. Early members of this lineage, like Prostosuchus, reached lengths exceeding 6 meters and weights that may have exceeded 2 tons. These were not the ancestors of dinosaurs, but their competitors, massive, quadrupedal predators that dominated terrestrial ecosystems for millions of years before the first true dinosaurs appeared. What made such gigantism possible was a unique combination of environmental and physiological factors that converged during Pangea's later history. The supercontinent's vast, stable continental environments provided extensive habitats where large animals could find sufficient resources. Unlike island environments, where large body size is typically disadvantageous due to limited resources, Pangea's continental scale allowed for the evolution of truly massive herbivores and the predators that hunted them. The early dinosaurs that appeared during the later Triassic period were initially modest in size, but they carried within their body plans the potential for unprecedented gigantism. Their erect limb posture, more efficient respiratory systems, and sophisticated circulatory adaptations would eventually allow some lineages to achieve sizes that exceeded any land animal before or since. The largest sauropod dinosaurs, though they evolved after Pangea's breakup, represented the fulfillment of evolutionary potential that first emerged during the supercontinent's existence. Theropsids, the mammal-like reptiles that dominated earlier Pangean ecosystems, also experimented with remarkable body sizes. Lassuacia, discovered in Poland and dating to the late Triassic, reached sizes comparable to modern African elephants. This massive dicynodont herbivore weighed an estimated 9 tons, making it one of the largest non-dinosaurian land animals ever discovered. Its existence suggests that the potential for gigantism was not limited to archosaurs, but represented a broader evolutionary trend during Pangea's later history. The physiological innovations that made such gigantism possible were remarkable achievements of evolutionary engineering. Large body size creates numerous challenges: how to pump blood to extremities, how to move efficiently despite increased mass, how to obtain and process sufficient food, and how to regulate body temperature in animals with unfavorable surface-area-to-volume ratios. The giant animals of Pangea solved these problems in ways that modern biology is still working to understand fully. Efficient respiratory systems were crucial for supporting the metabolic demands of giant land animals. Early archosaurs developed air sac systems similar to those found in modern birds, allowing for more efficient oxygen extraction and better regulation of body temperature. These innovations may have been essential for achieving the large body sizes that characterized later members of this group, including the massive dinosaurs that would dominate post-Pangean ecosystems. The feeding strategies of Pangea's giants were as impressive as their size. Massive herbivores like the dicynodonts developed sophisticated dental batteries and powerful jaw muscles, capable of processing enormous quantities of tough, fibrous plant material. Their digestive systems likely included massive fermentation chambers, where symbiotic bacteria helped break down cellulose, much like the digestive systems of modern ruminants, but on a scale that dwarfs anything alive today. Social behaviors among these giants may have been surprisingly complex. Fossil evidence suggests that some large Triassic archosaurs may have engaged in sophisticated parental care, territorial behaviors, and possibly even primitive forms of cooperative hunting. The stable, extensive habitats available on Pangea may have provided opportunities for the evolution of social complexity that would have been impossible in more fragmented landscapes. The evolutionary arms race between predators and prey drove both groups toward ever greater size during certain periods of Pangea's history. As herbivores grew larger to escape predation and more effectively compete for plant resources, predators responded by evolving their own gigantic forms. This feedback loop created some of the most spectacular predator-prey relationships in the history of terrestrial life. But gigantism came with costs as well as benefits. Large animals require vast territories and enormous amounts of food, making them vulnerable to environmental changes that might barely affect smaller species. The transition from Pangean to post-Pangean climates may have favored smaller, more adaptable animals over the giants that had dominated earlier ecosystems. Many of the largest Triassic animals went extinct during the End Triassic extinction event, paving the way for the evolution of dinosaurs. The breakup of Pangea itself may have contributed to the eventual evolution of the largest land animals ever. As the supercontinent fragmented, it created new coastal environments and more moderate climate conditions that could support the massive sauropod dinosaurs. These animals, reaching lengths exceeding 30 meters and weights that may have exceeded 50 tons, represented the ultimate expression of the gigantism trend that began during Pangea's existence. Modern reconstructions of Pangean ecosystems reveal landscapes dominated by animals that would seem fantastical if they didn't exist in the fossil record. Herds of elephant-sized dicynodonts browsing through forests of primitive conifers, massive crocodile-like archosaurs lurking in riverside environments, and early dinosaurs beginning their first tentative experiments with the body plans that would eventually produce the largest land animals of all time. The legacy of Pangean gigantism extends far beyond the fossil record. The evolutionary innovations that first appeared in these ancient giant-sufficient respiratory systems, sophisticated circulatory adaptations, and complex social behaviors provided the foundation for many of the most successful vertebrate groups in Earth's history. In a very real sense, the giants of Pangea were evolutionary pioneers whose innovations continued to shape life long, after the supercontinent itself had vanished into geological history.
Imagine a world where a determined traveler could walk from the frozen wastes of Antarctica to the tropical forests of Siberia without ever wading through water deeper than a river. This was the reality of life on Pangea supercontinent that served as Earth's first and only global highway, connecting ecosystems and enabling biological exchanges on a scale that has never been possible since. This continental unity created evolutionary opportunities that were unprecedented in Earth's history and remain impossible in our modern, ocean-divided world. Species that evolved in one corner of Pangea could spread across the entire supercontinent, colonizing new environments and adapting to different conditions while maintaining genetic connectivity across vast distances. The result was a level of biological cosmopolitanism that makes our modern concepts of endemic species seem almost quaint by comparison. The early archosaurs provide perhaps the clearest example of how Pangea's unity facilitated global distribution of species. Fossil evidence shows that certain archosaur species had ranges that spanned, literally, from one end of the supercontinent to the other. Esmatosichus, a heavily armored, crocodile-like reptile, has been found in rocks from what is now the southwestern United States to Germany, India, and Morocco. A distribution they would be impossible for any terrestrial animal in our current world. But the global highway functioned differently for different types of organisms. Large, mobile animals could take full advantage of Pangea's connectivity, spreading rapidly across continental distances and maintaining gene flow between distant populations. Smaller animals and plants faced different challenges and opportunities. While they couldn't cover the vast distances as quickly as larger species, they could still achieve remarkable distributions through gradual range expansion over geological time. The absence of oceanic barriers meant that evolutionary innovations could spread across the globe with unprecedented efficiency. New adaptations that appeared in one part of Pangea could quickly be transmitted to populations thousands of kilometers away, accelerating the pace of evolutionary change and creating feedback loops that enhanced biological diversity across the entire supercontinent. Climate gradients on Pangea created a natural testing ground for evolutionary adaptation. A species that evolved in the tropical regions near the Tethys Sea could gradually adapt to cooler conditions as it spread toward the polar regions of the supercontinent, or evolve desert adaptations as it moved into the arid interior. This continuous variation in environmental conditions, unbroken by oceanic barriers, allowed for the evolution of remarkably adaptable species with broad ecological tolerances. The concept of biogeographic provinces, distinct regional faunas separated by geographical barriers, was largely meaningless during Pangea's existence. Instead of the endemic species that characterize isolated continents in our modern world, Pangean ecosystems were dominated by cosmopolitan forms that could be found across multiple climate zones and habitat types. This created a kind of biological uniformity that has no modern parallel. River systems on Pangea served as particularly important corridors for biological dispersal. Unlike modern river systems that are confined to individual continents, Pangean rivers could potentially connect ecosystems across vast distances. A freshwater fish species that evolved in rivers flowing into the Tethys Sea could theoretically spread through interconnected drainage systems to rivers on the opposite side of the supercontinent. The migration patterns of Pangean animals would have been spectacular to witness. Without oceanic barriers to interrupt their movements, seasonal migrations could span continental distances. Some researchers speculate that certain archosaur species may have undertaken migrations that covered thousands of kilometers, following seasonal changes in temperature and resource availability across the supercontinent's vast expanse. Plant dispersal on Pangea operated on equally impressive scales. Wind-dispersed seeds and spores could travel unimpeded across continental distances, while animal-dispersed plants could spread through the activities of wide-ranging herbivores and seed-eating animals. This led to the evolution of plant communities with remarkably broad distributions, though local adaptations still created regional variations in forest composition and structure. The marine realm around Pangea was equally connected, but in different ways. Panthalassa, the superocean that surrounded the supercontinent, allowed for even more extensive biological connections than the land surface. Marine species could potentially circumnavigate the entire globe, leading to the evolution of oceanic ecosystems with even greater cosmopolitan character than their terrestrial counterparts. But Pangea's role as a global highway also had darker implications. Diseases and parasites could spread just as easily as their hosts, potentially creating pandemic events that affected entire continents. The lack of geographical barriers that facilitated biological exchange also meant that there were few refugia where species could escape from widespread environmental catastrophes or competitive pressures. The eventual breakup of Pangea brought this era of global biological connectivity to an abrupt end. As ocean basins opened and continents separated, species that had enjoyed continent-spanning distributions suddenly found themselves divided by growing seas. This geographic isolation triggered rapid speciation as separated populations adapted to their new, more limited environments. The transition from Pangean to post-Pangean Biogeography represents one of the most significant events in the history of life on Earth. The fragmentation of once continuous distributions led to the evolution of the endemic faunas that characterize modern continents. Madagascar's unique lemurs, Australia's marsupials, and South America's distinctive mammalian fauna all trace their origins to this great geographic isolation event. Modern conservation biology often focuses on creating corridors that connect fragmented habitats, recognizing that biological connectivity is essential for maintaining healthy ecosystems. In this context, Pangea represents the ultimate expression of habitat connectivity, a world where biological corridors span continents and species could maintain genetic contact across vast distances. Understanding how life functioned under these conditions of maximum connectivity provides valuable insights for managing our increasingly fragmented modern ecosystems. The legacy of Pangea's global highway lives on in the fossil record and in the biogeographic patterns we see today. The distribution of certain fossil groups across multiple continents makes sense only when we remember that those continents were once connected. Similarly, the genetic relationships between species on different continents often reflect their common ancestry on the unified supercontinent, preserved despite hundreds of millions of years of continental drift. In the shadowed margins where scientific orthodoxy meets speculative possibility, there exists a tantalizing question that challenges our understanding of deep time itself. Could the vast expanses of Pangea, stable for tens of millions of years, have witnessed the rise of complex civilizations that preceded not just humanity, but the very evolutionary lineages that would eventually give rise to intelligent life as we know it? This is not a question that mainstream science entertains seriously, and for good reasons. The timescales involved, hundreds of millions of years, seem to preclude any possibility of preserving evidence of complex technological civilizations. Yet some researchers working at the very edges of respectability have begun to ask whether our assumptions about the nature and longevity of advanced civilizations might be fundamentally flawed. Consider the puzzle of certain geological formations that seem to display organizational patterns too regular for natural processes, yet too ancient for any known biological explanation. The Klerksdorp spheres, found in 3-billion-year-old rock formations in South Africa, are nearly perfect metallic spheres with parallel grooves around their equators. While most geologists attribute these to natural mineral processes, their remarkable uniformity and geometric precision have led some to wonder whether they represent artifacts of technological activity from an almost unimaginably ancient past. During Pangea's existence, environmental conditions were stable enough to permit the development of complex ecosystems over geological timescales. Some archosaur species showed remarkable cognitive abilities, with brain-to-body ratios that approached those of modern birds and evidence of sophisticated social behaviors. While these animals were clearly not building civilizations in any sense we would recognize, they demonstrate that high intelligence could evolve under Pangean conditions. The concept of deep time presents particular challenges for detecting ancient technological civilizations. Even structures built from the most durable materials, stone, metal, ceramics, would be virtually undetectable after hundreds of millions of years of weathering, erosion, and geological recycling. The oldest human artifacts, dating back mere thousands of years, are preserved only under exceptional circumstances. What would remain of a technological civilization after 200 million years? Some theorists have proposed that the signatures of advanced civilizations might be preserved not in artifacts, but in geological anomalies. Unusual concentrations of rare elements, isotopic ratios that don't match natural processes, or mineral formations that seem to require technological intervention might represent the only detectable traces of Pangean civilizations. The problem is distinguishing such signatures from the myriad natural processes that can create equally anomalous geological features. The Permo-Triassic boundary layers, deposited during the Great Extinction, that marked the transition between Pangea's early and late periods contain chemical anomalies that have never been fully explained. Elevated concentrations of rare metals, unusual carbon isotope ratios, and mineral formations that seem to require extreme temperatures have all been documented. While most scientists attribute these to massive volcanism and environmental catastrophe, a few have wondered whether some signatures might reflect technological activity by civilizations that were themselves victims of the extinction event. If Pangean civilizations existed, they would have faced challenges utterly unlike those confronting human societies. The supercontinent's extreme interior deserts, massive storm systems, and periodic volcanic catastrophes would have required technological adaptations that might bear no resemblance to human technology. Perhaps such civilizations developed entirely different approaches to energy, materials, and environmental management that left no traces recognizable to our current scientific paradigms. The temporal isolation of Pangean civilizations would have been absolute. Unlike human civilizations, which can study archaeological remains of their predecessors, any technological societies on Pangea would have had no prior examples to study or build upon. They would have had to develop science, technology, and social organization entirely from first principles, a constraint that might have led to technological paths completely different from our own. Some researchers have noted that certain architectural features found in ancient human structures seem to incorporate knowledge of astronomical cycles and geological processes that would have been difficult to acquire through observation alone. While conventional archaeology explains these through the sophisticated observational capabilities of ancient civilizations, alternative theories suggest that some knowledge might represent information preserved from much older sources, possibly including pre-breakup Pangean civilizations whose astronomical observations would have been made under entirely different continental configurations. The distribution of certain mineral formations across multiple continents has occasionally raised eyebrows among geologists. Formations that appear in similar patterns on continents that were adjacent during Pangea's existence sometimes show evidence of modification or organization that seems too regular for natural processes. While these are typically attributed to shared geological history, a few researchers have wondered whether they might represent the remains of infrastructure projects that spanned continental distances. Modern deep-time geology has revealed that Earth's history includes periods of stability lasting tens of millions of years time scales that would allow for the rise, flourishing, and extinction of multiple successive civilizations. The late Carboniferous and early Permian periods during Pangea's formation represent one such stable interval. If intelligence and technology could evolve, these extended periods of environmental stability would have provided opportunities for civilizations to develop and mature. The absence of evidence is not necessarily evidence of absence, particularly when dealing with timescales that exceed human comprehension. The geological processes that have operated since Pangea's breakup, continental drift, mountain building, erosion, and sedimentation, have been thorough enough to erase most traces of surface features from that era. Even massive technological installations might have been ground down to unrecognizable mineral deposits or buried beneath kilometers of later sedimentary rocks. Perhaps most intriguingly, some researchers have suggested that the rapid evolutionary changes that occurred during certain periods of Pangea's history, sudden appearance of new species with sophisticated adaptations, might reflect not just natural selection, but some form of technological intervention. While this ventures deep into speculative territory, it raises questions about whether advanced civilizations might have experimented with biological engineering in ways that influenced the evolutionary trajectory of life on Earth. The search for Pangean civilizations remains firmly in the realm of speculation, constrained by the fundamental limitations of deep-time archaeology and the lack of any compelling physical evidence. Yet the questions raised by this speculative inquiry illuminate important aspects of how we think about intelligence, technology, and the preservation of information across geological time. Whether or not Pangean civilizations ever existed, Contemplating their possibility expands our understanding of what might be possible in the vast expanses of deep time that dwarf human history. Beneath the familiar landscapes of our modern world lie layers of ancient testimony, written in stone and preserved through hundreds of millions of years of geological transformation. These are not the easily readable records of recent history, but cryptic messages encoded in mineral formations, fossil assemblages, and geological structures that speak of Pangea's lost worlds and languages we are only beginning to understand. In the coal seams that power our industrial civilization lie the compressed remains of Pangean forests, so vast they stretched across continental distances. But these carbonized libraries contain more than just fossil plants. Embedded within the coal are microscopic traces of atmospheric chemistry, preserved pollen grains that speak of climate conditions, and even occasional fossils of the giant insects that ruled these ancient woodlands. Each coal seam represents thousands of years of forest growth, death, and burial, a compressed chronicle of life during one of the most biologically productive periods in Earth's history. The red sandstone formations that color the landscapes of the American Southwest, the Australian outback, and the deserts of North Africa are monuments to Pangea's arid interior. But these rocks contain puzzles that continue to challenge geological interpretation. Unusual mineral formations, unexpected chemical compositions, and structural features that seem to require conditions not fully explained by current models of desert formation all hint at environmental extremes that pushed the boundaries of what we consider geologically possible. In the ancient mountain belts that mark where Pangea's constituent continents collided, geologists have discovered mineral assemblages that preserve direct evidence of the pressures and temperatures that accompanied continental collision. Diamonds formed in the deep crust shocked quartz crystals that record the passage of seismic waves, more powerful than any modern earthquake, and metamorphic rocks that preserve the chemical signatures of collision events that reshaped entire regions in geological instants. Perhaps most mysteriously, certain geological formations from Pangea's era contain what scientists call exotic terrains, fragments of crust that seem to have originated in locations completely different from where they are now found. These geological nomads traveled thousands of kilometers during Pangea's assembly, carrying with them mineral signatures and fossil assemblages that provide glimpses of lost landscapes and extinct ecosystems that existed in places we can no longer identify. The Permian-Triassic boundary layers, deposited during the Great Extinction that marked a crucial transition in Pangea's history, contain some of the most puzzling geological signatures ever discovered. Unusual concentrations of rare metals like iridium and platinum, typically associated with extraterrestrial impacts, are mixed with chemical signatures of massive volcanism and environmental collapse. These boundary layers represent a geological crime scene where multiple catastrophes seem to have occurred simultaneously, creating a complex puzzle that researchers are still working to solve. Fossilized forests buried beneath layers of volcanic ash provide snapshot moments from Pangea's history, preserving entire ecosystems in exquisite detail. The petrified forest of Arizona contains trees that were alive during Pangea's later history, their cellular structure so perfectly preserved that researchers can study growth patterns, seasonal variations, and even evidence of disease and insect damage from 200 million years ago. These preserved forests are like ancient libraries where the stories of individual organisms have been frozen in stone. Underground, cave systems that formed during Pangea's existence preserve even more remarkable records. Speleothem stalactites and stalagmites formed from mineral-rich water contain chemical signatures that record changes in climate, atmospheric composition, and even volcanic activity over periods of millions of years. These underground archives are particularly valuable because they are protected from surface weathering and erosion, preserving environmental records with a resolution that rivals modern scientific instruments. The magnetic signatures preserved in Pangean rocks tells stories of a planet whose magnetic field behaved very differently than it does today. Periods of rapid magnetic reversals intervals, when the magnetic field strength dropped to nearly zero, and epochs when the magnetic poles wandered in patterns that suggest fundamental changes in the Earth's core dynamics, all left their marks in the mineral. Grains that crystallized during Pangea's existence. Sedimentary rocks from Pangean lake and river systems contain microscopic fossils that reveal the inner workings of ancient ecosystems with surprising detail. Pollen grains preserve information about plant communities. Microscopic animal remains document food web relationships. And chemical signatures in the sediments record everything from seasonal rainfall patterns to the frequency of forest fires. These microscopic archives often contain more detailed environmental information than the spectacular fossil skeletons that capture public attention. Perhaps most intriguingly, some geological formations from Pangea's time contain structures that seem to require explanation beyond simple physical and chemical processes. Regularly spaced mineral formations, geometric patterns in rock layers, and organized arrangements of geological features have occasionally led researchers to wonder whether biological processes, possibly involving species and behaviors unknown from the modern world, might have played larger roles in shaping Pangean landscapes than previously suspected. The isotopic signatures preserved in Pangean minerals tell complex stories about the cycling of elements through ancient ecosystems. Carbon isotope ratios reveal information about photosynthetic processes and atmospheric composition. Oxygen isotopes preserve records of ancient temperatures and water chemistry. And sulfur isotopes document the activity of ancient microbial communities. These chemical fingerprints provide quantitative data about environmental conditions during specific intervals of Pangea's history. Underground water trapped in ancient rock formations, some of it potentially dating back to Pangea's existence, represents another type of geological archive. This fossil water preserves dissolved minerals and chemical signatures that reflect the atmospheric and surface conditions that existed when it was originally incorporated into the rock. Analyzing such ancient water provides direct chemical sampling of Pangean environments, offering insights that complement the indirect evidence preserved in minerals and fossils. The challenge of interpreting these geological archives lies in learning to read languages written in chemistry, physics, and biology across timescales that exceed human comprehension. Each rock formation, mineral deposit, and fossil assemblage represents a document written in the Earth's own script, preserving information about worlds that vanished millions of years before the first humans appeared. Understanding these messages requires translating between the rapid timescales of biological processes and the vast timescales of geological change, bridging scales of space and time that challenge the limits of human comprehension. As analytical techniques become more sophisticated, researchers continue to extract new information from these ancient archives, revealing details about Pangean environments and ecosystems that seemed forever lost to deep time. Each new discovery adds another piece to the puzzle of understanding what life was like on the supercontinent, building a picture of Earth's past that becomes more complete and more remarkable with each advance in geological detective work. At the very peak of Pangea's dominance, when the supercontinent had reached its maximum extent and life had adapted to its extreme continental conditions, disaster struck with a thoroughness that nearly ended complex life on Earth entirely. The end Permian extinction event, occurring roughly 252 million years ago, was a catastrophe so complete that paleontologists call it the Great Dying, an extinction that eliminated approximately 90% of marine species and 70% of terrestrial vertebrates in what may have been the closest approach to planetary sterilization in Earth's history. The scale of destruction was unprecedented and remains unmatched by any subsequent extinction event. To put this in perspective, the famous extinction that eliminated the dinosaurs 6.6 million years ago was merely a moderate crisis compared to the devastation that swept across Pangea at the end of the Permian period. Entire ecosystems vanished without trace evolutionary lineages that had dominated the Earth for tens of millions of years were erased completely, and the biological diversity that had accumulated over the previous 300 million years was reduced to a small fraction of surviving species that would have to rebuild life as complexity from nearly nothing. The cause of this catastrophe appears to have been the massive volcanic activity of the Siberian traps. But the extinction was not simply a matter of lava flows destroying local ecosystems. Instead, the volcanism triggered a cascade of environmental changes that transformed Earth's atmosphere, oceans, and climate in ways that made survival nearly impossible for most forms of complex life. The volcanic emissions created a cocktail of environmental toxins that poisoned air, land, and sea simultaneously. Massive injections of carbon dioxide from the volcanic eruptions created rapid greenhouse warming that raised global temperatures by as much as 8 to 10 degrees Celsius. This temperature increase was not gradual, but occurred over a geologically brief period of perhaps 20,000 years, rapid enough to prevent most species from adapting to the new conditions. The warming was particularly severe in polar regions, eliminating the temperature gradients that drive global circulation patterns and creating a world where heat stress affected organisms from equator to pole. Simultaneously, volcanic emissions of sulfur compounds created acid rain on a planetary scale. The acidity of precipitation increased dramatically, poisoning freshwater ecosystems and leaching nutrients from soils across vast regions of Pangea's surface. Plants, already stressed by extreme temperatures, found themselves unable to maintain basic physiological functions in increasingly toxic environments. Perhaps most devastating of all were the changes in ocean chemistry that accompanied the terrestrial catastrophe. The massive carbon dioxide emissions acidified seawater to levels that dissolved the calcium carbonate shells and skeletons of marine organisms. Coral reefs, which had been among Earth's most diverse ecosystems, were completely eliminated. Marine ecosystems that had evolved intricate food webs over hundreds of millions of years collapsed as their foundational species were chemically dissolved by their own environment. Ocean temperatures rose to lethal levels in many regions, while changing circulation patterns created vast dead zones depleted of oxygen. Marine organisms that survived the initial chemical assault often found themselves in waters that could no longer support complex life. The fossil record from this period shows a dramatic shift from diverse marine communities to simple bacterial mats, a return to ecological conditions not seen since Earth's earliest history. On land, Pangea's unique geography may have made the extinction even more severe than it would have been on a more fragmented planet. The supercontinent's vast interior regions, already stressed by extreme climate conditions, became completely uninhabitable as temperatures soared beyond the tolerance limits of virtually all large animals and plants. Unlike extinction events on fragmented continents, where some regions might escape the worst effects and serve as refugia for surviving species, Pangea's continental unity meant that environmental catastrophes could affect the entire landmass simultaneously. The atmospheric composition itself became toxic to many forms of life. In addition to elevated carbon dioxide and sulfur compounds, volcanic emissions may have included hydrogen sulfide, a gas that is poisonous to most oxygen-breathing organisms at relatively low concentrations. Some researchers suggest that hydrogen sulfide concentrations became high enough to penetrate the stratosphere, where they could have destroyed the ozone layer and exposed Earth's surface to lethal levels of ultraviolet radiation. The extinction was not an instantaneous event, but unfolded over a period of perhaps 60,000 years, brief in geological terms, but long enough to create multiple phases of environmental stress. Species that survived the initial volcanic catastrophe might have been eliminated by subsequent climate changes, ocean acidification, or secondary effects like ecosystem collapse and food web disruption. The prolonged nature of the crisis meant that even species with considerable resilience were eventually overwhelmed. Fungal spores dominate the fossil record from the immediate aftermath of the extinction, suggesting that decomposer organisms briefly inherited a world carpeted with the remains of its former inhabitants. These fungal spikes in the geological record indicate that dead organic matter was so abundant that it supported explosive growth of decay organisms, grim testimony to the thoroughness of the ecological collapse. The few vertebrate species that survived the Great Dying were mostly small, generalized forms that could survive on limited resources and tolerate extreme environmental conditions. Many of these survivors were early archosaurs and therapsids groups that would eventually give rise to dinosaurs and mammals, respectively. In a very real sense, the end Permian extinction cleared the evolutionary stage for the rise of the animal groups that would dominate the Mesozoic era. Recovery from the extinction was remarkably slow, taking perhaps 10 million years for ecosystems to regain even a fraction of their former complexity. This prolonged recovery period suggests that the environmental damage was so severe that it fundamentally altered Earth's capacity to support diverse life. The early Triassic period, which followed the extinction, was characterized by low-diversity ecosystems dominated by disaster taxo-opportunistic species that could thrive in degraded environments. The Great Dying represents more than just a biological catastrophe. It was a fundamental reset of Earth's evolutionary trajectory. The ecosystems that had characterized Pangea's earlier history, dominated by synapsids and early reptilian forms, were replaced by entirely different biological communities. The extinction marked the end of the Paleozoic era and the beginning of the Mesozoic, ushering in the age of dinosaurs, and fundamentally altering the course of evolution for the next 200 million years. Modern research continues to reveal new aspects of this ancient catastrophe, using increasingly sophisticated techniques to understand exactly how environmental changes translated into biological extinction. Each new discovery adds to our understanding of how planetary-scale environmental catastrophes can reshape life, providing crucial insights for understanding modern climate change and environmental degradation. The Great Dying serves as a permanent reminder that even the most successful ecosystems and evolutionary lineages are vulnerable to sufficiently severe environmental disruption. Deep within the ancient rocks of Pangea lies a hidden library of information, written in the language of magnetism itself. As molten rock cooled and crystallized, as sediments settled layer by layer on ancient seafloors and lake beds, tiny magnetic minerals aligned themselves with Earth's magnetic field like microscopic compass needles, preserving a record of our planet's magnetic behavior across hundreds of millions of years. These mineral archives contain some of the most remarkable and puzzling evidence about conditions on Pangea that scientists have ever discovered. The story begins with understanding that Earth's magnetic field is not the stable, predictable phenomenon that our modern experience suggests. Over geological time, the magnetic field has undergone dramatic reversals, where north and south poles switch places, periods of intense strengthening and weakening, and episodes of chaotic wandering where the magnetic poles move thousands of kilometers from their expected positions. During Pangea's existence, magnetic behavior was particularly turbulent, creating a record that challenges our understanding of how planetary magnetic fields operate. Paleomagnetic studies of Pangean rocks reveal that the supercontinent experienced some of the most rapid magnetic field reversals in Earth's recorded history. During certain periods, the magnetic field switched polarity multiple times within intervals of less than 1 million years, extraordinarily rapid by geological standards. These frequent reversals created a complex pattern of magnetic stripes in the rocks, like a geological barcode that records the planet's magnetic instability during Pangea's assembly and early history. But perhaps most intriguingly, the magnetic record suggests that Pangea may have influenced Earth's magnetic field generation in ways that scientists are only beginning to understand. The formation of the supercontinent altered the distribution of mass within Earth's crust and upper mantle, potentially affecting the convection patterns in the liquid iron outer core, where the magnetic field is generated. Computer models suggest that such changes could have destabilized the magnetic field generation process, leading to the turbulent magnetic behavior recorded in Pangean rocks. The magnetic inclination recorded in ancient rocks, the angle at which magnetic field lines intersected Earth's surface, provides crucial information about Pangea's position relative to the magnetic poles over time. This data has revealed that the supercontinent underwent significant latitudinal movement during its existence, drifting across climate zones in ways that help explain the dramatic environmental changes recorded in its geological history. At times, portions of Pangea that are now in temperate latitudes were positioned over the magnetic equator, experiencing tropical conditions that supported very different ecosystems than exist there today. Some of the most mysterious magnetic signatures in Pangean rocks are associated with periods of rapid environmental change and mass extinction. The end Permian extinction event, for instance, coincides with a period of particularly chaotic magnetic field behavior, including extended intervals of weakened field strength and rapid directional changes. Some researchers have speculated that magnetic field instability might have contributed to the extinction by reducing Earth's protection from cosmic radiation, or by disrupting the navigation systems of migrating organisms. The apparent polar wander paths reconstructed from Pangean paleomagnetic data tell a remarkable story of continental drift and magnetic pole movement. These paths show that Pangea not only moved as a single unit, but also rotated significantly during its existence, changing its orientation relative to Earth's rotational axis. Such movements would have had profound effects on climate patterns, ocean circulation, and the distribution of solar radiation across the supercontinent's surface. Certain magnetic anomalies in Pangean rocks have proved difficult to explain using conventional models of magnetic field generation. Patches of rocks with magnetic orientations that seem inconsistent with their geological age regions, where magnetic intensity varies dramatically over short distances and formations that preserve evidence of multiple magnetic events occurring simultaneously, all suggest that magnetic field behavior during Pangea's time was more complex than current theory predicts. The magnetic properties of Pangean volcanic rocks provide particularly detailed records of ancient magnetic field behavior because volcanic materials crystallize rapidly and preserve nearly instantaneous snapshots of magnetic conditions. Studies of these rocks have revealed that magnetic field intensity during certain periods of Pangea's history was significantly different from modern values, sometimes much stronger, sometimes much weaker, and occasionally approaching zero during magnetic reversals. Recent research has discovered that some Pangean rocks preserve evidence of extremely rapid magnetic field changes alterations that occurred over periods of decades or centuries rather than the thousands or millions of years typically associated with magnetic variations. These rapid changes, if confirmed, would require fundamental revisions to our understanding of how Earth's magnetic field operates, and suggest that the core dynamics during Pangea's time were fundamentally different from modern conditions. The relationship between magnetic field behavior and climate during Pangea's existence remains an active area of research. Some studies suggest that periods of weakened magnetic field strength correlate with episodes of rapid climate change, possibly because reduced magnetic shielding allowed increased cosmic radiation to reach Earth's atmosphere, where it could influence cloud formation and atmospheric chemistry. If confirmed, this connection would add another layer to the complex environmental changes that characterized Pangea's history. Magnetic minerals and sedimentary rocks from Pangean lake and river systems preserve records of local magnetic field variations that provide insights into environmental conditions with remarkable temporal resolution. These records show that magnetic field behavior varied not just over millions of years, but also on much shorter timescales, possibly responding to changes in local geology, hydrothermal activity, or even biological processes. The implications of Pangea's magnetic record extend far beyond academic interest in ancient magnetic field behavior. Understanding how magnetic fields respond to large-scale changes in Earth's surface configuration provides crucial insights for predicting how ongoing continental drift and climate change might affect magnetic field stability in the future. The magnetic chaos that accompanied Pangea's formation and breakup may provide a preview of magnetic field changes that could occur during future supercontinent cycles. Modern analytical techniques continue to extract increasingly detailed information from Pangea's magnetic archives, revealing new aspects of magnetic field behavior that were previously impossible to detect. Each new discovery adds to our understanding of how planetary magnetic fields operate under extreme conditions, and how changes in Earth's surface configuration can influence processes operating deep within our planet's interior. The magnetic whispers preserved in Pangean rocks continue to reveal secrets about one of our planet's most fundamental and mysterious processes. Above the strange landscapes of Pangea stretched skies that would have appeared alien to any observer familiar with our modern world. The very atmosphere that enveloped the supercontinent was different in composition, density, and optical properties, creating celestial phenomena and atmospheric effects that have no contemporary equivalent. Understanding these ancient skies provides crucial insights into how environmental conditions on Pangea influenced the evolution of life and shaped the character of the supercontinent's unique ecosystems. The atmospheric composition during much of Pangea's existence was radically different from today's. Oxygen levels fluctuated dramatically, sometimes reaching concentrations of 35% compared to our modern 21%, while carbon dioxide levels varied from near-modern values to concentrations that were 10 times higher. These compositional differences affected everything from the color of the sky to the behavior of weather systems, and the very nature of combustion and respiration on the planet's surface. During periods of high atmospheric oxygen, the sky itself would have appeared subtly different. Higher oxygen concentrations affect the scattering of light by atmospheric molecules, potentially creating skies with different hues and optical properties than those we observe today. Sunsets and sunrises during the high oxygen periods might have displayed color spectra shifted toward the blue end of the spectrum, while the overall sky color during midday hours could have had a different tonal quality. The increased atmospheric density that accompanied high oxygen and carbon dioxide levels would have created optical effects unknown in our modern world. Atmospheric refraction would have been more pronounced, potentially making objects on the horizon appear larger and closer than they actually were. This enhanced refraction might have created superior mirages and other atmospheric optical phenomena that were common features of Pangean skies. Lightning during Pangea's massive thunderstorms would have behaved differently in the altered atmospheric conditions. Higher oxygen concentrations would have made the atmosphere more electrically conductive, potentially allowing for longer-lasting and more intense electrical discharges. The color and characteristics of lightning might have been noticeably different, with electrical phenomena that have no modern equivalent occurring during the supercontinent's massive storm systems. The astronomical cycles that govern Pangea's climate were significantly different from those affecting our modern world due to changes in Earth's orbital parameters and rotational characteristics over geological time. The length of Earth's day during Pangea's existence was shorter than today, approximately 22 hours instead of 24 due to tidal friction effects that have gradually slowed our planet's rotation. This faster rotation would have affected everything from the Coriolis effect, driving weather patterns, to the apparent motion of celestial objects across Pangean skies. The moon appeared larger in Pangean skies because it was closer to Earth during the supercontinent's existence. Tidal forces were correspondingly stronger, creating more extreme tides than those we experience today. The enhanced tidal effects may have played important roles in shaping coastal ecosystems and influencing the evolution of marine organisms during Pangea's history. The larger apparent size of the moon would also have made lunar eclipses more spectacular and solar eclipses more frequent and dramatic. Meteoric activity was likely more intense during certain periods of Pangea's existence due to the solar system's passage through regions of space with higher concentrations of debris. The altered atmospheric composition would have affected how meteors appeared as they burned up in the atmosphere, potentially creating meteor showers with different visual characteristics than those observed today. Some researchers speculate that major meteor impacts during Pangea's history may have contributed to environmental changes and extinction events. The aurora phenomena that occurred during Pangea's time may have been more spectacular and frequent than modern displays due to differences in magnetic field behavior and atmospheric composition. The enhanced oxygen levels in the upper atmosphere could have created auroral displays with different colors and intensities, while the hungry magnetic field instability characteristic of Pangea's era might have allowed auroras to be visible at latitudes where they never appear in our modern world. Volcanic activity during Pangea's history would have created atmospheric effects on scales that dwarf anything observed in historical times. Major volcanic episodes could have injected enough particulate matter into the atmosphere to create spectacular sunsets and sunrises across entire hemispheres, while also reducing overall sunlight levels and creating cooling effects that lasted for years. The massive Siberian Traps volcanism may have created atmospheric conditions similar to a perpetual volcanic winter. The seasonal variations in Pangean skies would have been extreme due to the supercontinent's vast latitudinal extent and the absence of oceanic moderation. During summer in the northern portions of Pangea, the sun would have traced paths across the sky that remained high for months at a time, creating periods of nearly continuous daylight in polar regions. Conversely, winter darkness in these same regions would have been correspondingly severe and prolonged. Atmospheric pressure at Pangea's surface was higher than modern values due to the altered atmospheric composition, which would have affected the boiling point of water and the behavior of sound waves. Sound could have traveled further and with different characteristics in the denser atmosphere, potentially affecting animal communication systems and creating acoustic environments unlike anything in our modern world. The interaction between Pangea's unique atmospheric conditions and its extreme geography created weather phenomena that have no modern analogs. Massive high-pressure systems could have created clear skies that persisted for months across continental-scale regions, while the absence of oceanic moderation allowed for temperature extremes that created atmospheric disturbances visible as shimmering heat mirages across thousands of square kilometers. Dust storms in Pangea's interior regions would have created atmospheric effects that temporarily transformed the appearance of vast areas. These storms could have lofted enough material into the upper atmosphere to affect sky color and visibility across entire continents, creating reddish or brown-tinted skies that persisted for weeks after major dust events. The study of ancient atmospheric conditions preserved in geological formations continues to reveal new information about Pangean skies. Air bubbles trapped in amber, chemical signatures in sedimentary rocks, and isotopic compositions of ancient minerals all provide clues about atmospheric composition and behavior during different periods of the supercontinent's history. Each new discovery adds to our understanding of how radically different Earth's atmospheric conditions were during this remarkable period in our planet's history. In the realm where scientific speculation meets mythological possibility, there exists a tantalizing question that has captivated researchers working at the very edges of orthodox thinking. Could the persistent legends of Atlantis, that technologically advanced civilization that supposedly vanished beneath the waves, represent not fiction or allegory, but a deeply distorted cultural memory of actual lands that disappeared when Pangea fragmented and the modern oceans opened? The conventional interpretation of Atlantis, as presented in Plato's dialogues, places the lost continent in the Atlantic Ocean beyond the Pillars of Hercules, describing it as an advanced maritime civilization that was swallowed by the sea in a single day and night. Most scholars consider this to be either a philosophical allegory or a fictional narrative designed to illustrate political points about ideal societies and their potential for corruption and decline. Yet when we examine Plato's description through the lens of geological deep time, certain details become remarkably prescient. The notion of a large landmass in the Atlantic that disappeared beneath the ocean is, in a very real sense, an accurate description of what happened when Pangea broke apart and the Atlantic Ocean opened. Vast areas that had been dry land for hundreds of millions of years were indeed swallowed by the sea as continental rifting created new ocean basins. The time frame, however, presents obvious difficulties. Plato placed Atlantis' destruction approximately 9,000 years before his own time, while the breakup of Pangea occurred roughly 200 million years ago. No known mechanism could preserve accurate historical accounts across such temporal distances. Yet some researchers have wondered whether certain types of information might be encoded in ways that could survive across geological timescales. Consider the possibility that advanced civilizations might have developed on Pangea during its most stable periods, when environmental conditions remained relatively constant for millions of years. Such civilizations would have had access to resources and geographic stability unknown to any society in our fragmented modern world. They could have developed technologies and accumulated knowledge over timescales that dwarf human history, potentially achieving sophistication levels that would seem almost magical from our contemporary perspective. The geological record does preserve hints of phenomena that are difficult to explain through conventional natural processes. Certain mineral formations show evidence of extreme temperatures and pressures that seem to require technological intervention. Isotopic signatures in some ancient rocks suggest chemical processes that don't match known natural mechanisms. While mainstream science attributes these anomalies to exotic geological processes, a few researchers have wondered whether they might represent the traces of technological activity by civilizations that preceded our current understanding of Earth as biological history. If Pangean civilizations existed, their technological development would have been constrained by the supercontinent's unique environmental conditions. The extreme interior deserts, massive storm systems, and periodic volcanic catastrophes would have required technological adaptations completely different from anything developed by human societies. Perhaps such civilizations evolved technologies based on principles we haven't discovered, leaving traces that we don't recognize because they operate according to different physical paradigms. The concept of technological signatures surviving across geological time presents fascinating theoretical challenges. While artifacts made from conventional materials would be completely destroyed by weathering and erosion over such time periods, technologies based on exotic physics or materials science might leave more subtle traces. Modifications to crystal structures in minerals, artificial isotopic signatures in rock formations, or organizational patterns in geological features might represent the only detectable remains of pre-breakup technological activity. Some researchers have noted that certain aspects of human mythology and folklore contain remarkably accurate information about geological processes that would have been difficult to observe directly. Stories of lands rising and sinking, of connections between continents that are now separated by oceans, and of catastrophic changes in global geography appear in cultures worldwide. While these similarities are typically attributed to universal psychological archetypes or shared experiences of local geological events, alternative theories suggest they might preserve fragments of much older information. The distribution patterns of certain myths and legends across modern continents, sometimes seen to follow the geographical relationships that existed when those continents were part of Pangea. Flood stories with similar structural elements appear in cultures on continents that were adjacent during the supercontinent's existence, but are now separated by vast oceans. While conventional anthropology explains these similarities through cultural diffusion or psychological universals, some researchers have speculated about the possibility of much deeper historical connections. Archaeological anomalies occasionally surface that challenge conventional timelines of technological development. Sophisticated metallurgy, precise astronomical observations, and architectural achievements that seem to exceed what should have been possible for their purported time periods all appear in the archaeological record. While mainstream archaeology typically resolves these anomalies through revised understanding of ancient capabilities, alternative theories suggest they might represent fragments of much older technological traditions. The mathematical and astronomical knowledge encoded in ancient monuments sometimes demonstrates understanding of cycles and relationships that would have required centuries or millennia of careful observation to develop. The precision of certain astronomical alignments, the accurate incorporation of complex mathematical constants, and the demonstration of geographical knowledge that seems to exceed what should have been available to ancient civilizations all contribute to questions about the ultimate sources of such information. Modern deep ocean exploration has revealed geological features on the seafloor that preserve traces of landscapes that existed when current ocean basins were dry land. Submarine canyons that seem to have been carved by rivers' sedimentary formations that suggest terrestrial environments, and mineral deposits that appear to have formed under atmospheric conditions all provide evidence of the vast land areas that disappeared when Pangea fragmented. The search for Pangean Atlantis remains firmly in the realm of speculation, constrained by the fundamental challenges of preserving and recognizing technological signatures across geological time. Yet the questions raised by this inquiry illuminate important aspects of how information can be preserved and transmitted across vast temporal distances. Whether Atlantis represents distorted memories of Pangean civilizations or purely mythological constructions, the possibility reminds us that our planet's deep history may contain chapters we have not yet learned to read. The legacy of this speculative inquiry lies not in any definitive answers about ancient civilizations, but in its contribution to expanding our concepts of what might be possible in deep time. By considering how technological societies might develop under radically different environmental conditions and how their traces might survive across geological timescales, we develop more sophisticated understanding of the relationship between civilization, technology, and planetary history. In the sterile laboratories where scientists decode Earth's deepest secrets, a revolution in our understanding of Pangea continues to unfold through technologies that can extract information from the most unlikely sources. Ancient ice cores drilled from Antarctica contain atmospheric samples that date back hundreds of thousands of years, while sophisticated chemical analysis of microscopic mineral grains can reveal environmental conditions from hundreds of millions of years ago. These modern detective techniques are rewriting the story of Pangea, revealing details about the supercontinent that seem almost impossibly precise, considering the vast spans of time involved. The ice cores extracted from Antarctica's deepest layers represent one of the most remarkable archives of ancient atmospheric conditions available to modern science. While the oldest ice cores extend back only about 1 million years far short of Pangea's timeline, they provide crucial calibration data for understanding how atmospheric composition affects climate systems. By studying how modern atmospheric changes are recorded in ice, scientists can better interpret the chemical signatures of ancient atmospheres preserved in other geological formations. But the real treasure troves of Pangean information lie in the mineral grains and chemical signatures preserved in sedimentary rocks from the supercontinent's era. Zircon crystals, virtually indestructible mineral formations that can survive billions of years of geological recycling, preserve isotopic signatures that reveal information about the temperature, pressure, and chemical conditions under which they formed. These microscopic time capsules contain data about Pangean environments encoded at the atomic level. Oxygen isotope ratios in ancient minerals provide quantitative measurements of prehistoric temperatures with remarkable precision. By analyzing the ratios of different oxygen isotopes in fossilized shells, ancient soils, and mineral formations, scientists can reconstruct temperature profiles for specific regions of Pangea with accuracy measured in degrees Celsius. These measurements reveal that temperature extremes on the supercontinent were even more severe than previously suspected, with some regions experiencing conditions that exceeded the tolerance limits of virtually all modern life forms. Carbon isotope signatures preserved in organic compounds and carbonates tell detailed stories about ancient atmospheric composition and biological activity. The carbon isotope ratios in coal seams formed from Pangean forests reveal information about atmospheric carbon dioxide levels, plant physiology, and ecosystem productivity. These chemical fingerprints show that atmospheric composition during Pangea's existence fluctuated much more dramatically than previously thought, with some periods experiencing carbon dioxide levels that would have created greenhouse conditions capable of supporting tropical vegetation in polar regions. Sulfur isotope analysis has revealed evidence of massive volcanic events that dwarf anything in recorded human history. The sulfur signatures preserved in sedimentary layers from the end Permian period document volcanic emissions so massive that they altered the chemistry of the entire global ocean. These chemical traces provide quantitative measurements of the scale of volcanism that accompanied Pangea's later history, confirming that the Siberian Traps eruptions were indeed catastrophic enough to trigger the Great Dying Extinction event. Trace element analysis of ancient rocks has uncovered evidence of environmental conditions that challenge conventional understanding of Pangean ecosystems. Elevated concentrations of rare metals in certain sedimentary layers suggest periods of enhanced weathering and erosion that imply extreme climate conditions. Some formations contain trace element signatures that seem to require explanations beyond conventional geological processes, though interpretations of these anomalies remain controversial. Paleosol analysis, the study of fossilized ancient soils, provides detailed information about terrestrial conditions on Pangea, with spatial resolution measured in meters rather than continents. Chemical analysis of paleosols can reveal information about rainfall patterns, seasonal temperature variations, vegetation types, and even the atmospheric composition under which ancient soils formed. These studies have revealed that soil formation processes on Pangea operated under environmental conditions that have no modern analogs. Molecular fossil analysis has pushed the boundaries of what seemed possible in terms of preserving organic information across geological time. Certain organic molecules can survive for hundreds of millions of years under the right preservation conditions, maintaining their chemical structure sufficiently to provide information about the organisms that produced them. Analysis of molecular fossils from Pangean rocks has revealed details about ancient ecosystems, including information about organisms that left no conventional fossil remains. Magnetostratigraphy, the study of magnetic field reversals preserved in rock layers, provides precise timing information that allows scientists to correlate events across different regions of Pangea with unprecedented accuracy. By matching magnetic reversal patterns in rocks from different continents, researchers can determine exactly when various geological and biological events occurred relative to each other, creating a temporal framework for understanding Pangean history with resolution measured in thousands rather than millions of years. Fluid inclusion analysis involves studying tiny droplets of ancient water and gases trapped within mineral crystals as they formed. These microscopic time capsules preserve actual samples of Pangean atmosphere and groundwater, providing direct chemical analysis of environmental conditions from hundreds of millions of years ago. Some fluid inclusions contain atmospheric gases from Pangea's time, allowing researchers to measure ancient atmospheric composition with the same precision used to analyze modern air samples. Advanced imaging techniques using electron microscopy and X-ray crystallography can reveal structural details in fossils and minerals at the cellular and molecular level. These techniques have uncovered preservation of cellular structures in Pangean fossils that provide information about the physiology and biochemistry of ancient organisms. Some preserved cellular details are so complete that they reveal information about metabolic processes and environmental adaptations in organisms that lived hundreds of millions of years ago. Computational modeling integrated with geochemical data allows scientists to reconstruct Pangean environmental conditions with sophistication that approaches modern meteorological forecasting. By combining chemical signatures from multiple sources with computer simulations of atmospheric and oceanic circulation, researchers can create detailed models of climate systems, weather patterns, and environmental conditions across different regions of the supercontinent. The integration of data from multiple analytical techniques creates synergistic insights that exceed what any single method could provide. When oxygen isotope temperature measurements are combined with carbon isotope atmospheric data, paleosol analysis, and magnetic field timing information, the result is a multidimensional picture of Pangean environments that approaches the detail available for much more recent geological periods. Each new analytical technique that becomes available opens new windows into Pangean history, often revealing information it was considered forever lost to deep time. As technology continues to advance, the resolution and precision of Pangean environmental reconstructions continue to improve, bringing this ancient world into focus with clarity that would have been unimaginable just decades ago. The secrets trapped in ice and stone continue to yield their information to increasingly sophisticated scientific detective work, ensuring that our understanding of Pangea will continue to evolve and deepen for years to come. Imagine awakening tomorrow in a world where the breakup of Pangea never occurred, where a single vast landmass still dominates Earth's surface, surrounded by an endless ocean that stretches unbroken to every horizon. This is not merely a geological thought experiment, but a profound exploration of how continental configuration shapes everything from weather patterns and biological diversity to human culture and technological development. Understanding what our world would be like if Pangea still existed provides crucial insights into how geography influences the fundamental character of planetary civilization. The climate of a modern Pangea would be characterized by extremes that dwarf anything experienced in our contemporary world. The supercontinent's vast interior regions would be scorching deserts where temperatures regularly exceeded 60 degrees Celsius during summer months, creating conditions lethal to most forms of complex life. Without oceanic moderation, seasonal temperature swings would be enormous. Interior regions that reached killing heat in summer could plummet to Arctic conditions during winter months, creating thermal cycling that would challenge even the most adaptable organisms. Monsoon systems on a Pangean world would be meteorological phenomena of unprecedented scale. The seasonal temperature differences between the vast landmass and the equally vast surrounding ocean would create pressure gradients capable of driving winds at velocities that have no modern equivalent. These supermonsoons could transport moisture thousands of kilometers inland, creating seasonal deluges that would reshape entire regions annually while leaving other areas in perpetual drought shadow. Human civilization, had it evolved on such a world, would have developed along radically different trajectories. The absence of oceanic barriers would have allowed for unprecedented cultural and genetic exchange across vast distances, potentially creating a global civilization much earlier in human development. Languages, technologies, and cultural practices could have spread across continental distances without the isolation that created the diversity of human cultures in our actual world. Alternatively, the extreme environmental gradients on Pangea might have created forms of geographic isolation even more severe than oceanic barriers. The vast interior deserts could have been as impassable as oceans, while the extreme seasonal variations might have required human populations to develop highly specialized adaptations for specific environmental zones. Instead of island cultures separated by water, Pangean humanity might have evolved as oasis cultures separated by uninhabitable wastelands. The biological diversity of a modern Pangea would be fundamentally different from our current world. The absence of geographic isolation that drives speciation on separated continents would have prevented the evolution of the endemic faunas that characterize modern biogeography. Instead of the distinctive mammals of Australia, the unique birds of Madagascar, or the specialized plant communities of isolated mountain ranges, a Pangean world would likely be dominated by cosmopolitan species with enormous geographic ranges. Transportation and trade on Pangea would operate according to entirely different principles than those governing our ocean-divided world. Instead of maritime commerce connecting distant ports, continental trade routes could span unbroken distances from one side of the world to the other. Caravans could theoretically travel from equatorial regions to polar zones without crossing water, though the extreme climate variations might make such journeys practically impossible during certain seasons. The technological development of Pangean civilization would likely have been profoundly influenced by the continent's environmental extremes. Energy systems would need to cope with extreme temperature variations and powerful seasonal storms. Architecture would require designs capable of withstanding both scorching heat and bitter cold, as well as the massive dust storms and seasonal floods that would characterize different regions. Water management would be crucial for survival in the vast interior deserts, potentially driving early development of sophisticated hydraulic technologies. Military strategy and geopolitics on Pangea would operate on scales that dwarf anything in our recorded history. Empires could potentially span distances equivalent to traveling from London to Beijing without crossing water, but controlling such vast territories would present logistical challenges beyond anything attempted in our world. The extreme interior regions might serve as natural barriers as effective as oceans, creating geographic constraints on political expansion despite the theoretical absence of water barriers. Resource distribution across Pangea would create economic patterns completely unlike those in our maritime world. Instead of islands rich in specific resources, separated by ocean from markets and processing centers, Pangean resources would be distributed across a continuous landmass where transportation costs would depend on overland distances and the challenges of traversing extreme environments rather than maritime shipping capabilities. The evolution of plant and animal domestication would likely have proceeded very differently on Pangea. The geographic connectivity that would have prevented speciation might also have prevented the development of the diverse crop varieties and livestock breeds that characterize our world. Alternatively, the extreme environmental gradients might have driven the evolution of species with remarkable adaptability, potentially providing Pangean agriculture with crops capable of thriving across a much wider range of conditions than modern varieties. Seasonal migration patterns on Pangea could have operated on continental scales unknown in our current world. Animal populations might have undertaken migrations spanning thousands of kilometers as they followed seasonal changes in temperature and precipitation across the supercontinent. These mega migrations could have been among the most spectacular biological phenomena on the planet, involving millions of individuals moving across distances that would require crossing multiple modern countries. The oceans surrounding Pangea would be a very different environment from our modern oceans divided by continental barriers. Panthalassa would allow for oceanic circulation patterns and marine ecosystems operating on truly global scales. Marine species could potentially circumnavigate the entire planet, while ocean currents unimpeded by continental barriers might create circulation patterns capable of moderating global climate more effectively than our current compartmentalized ocean systems. Weather prediction on Pangea would be both simpler and more complex than in our modern world. Simpler because storm systems could develop across much larger areas without interference from oceanic barriers, potentially making long-range patterns more predictable. More complex because the sheer scale of meteorological phenomena would create weather systems so large that their behavior might be influenced by factors that don't affect smaller-scale modern weather patterns. The psychological and cultural implications of living on Pangea would be profound. The knowledge that one could theoretically walk to any place on Earth might create very different concepts of distance, isolation, and cultural identity than those that developed in our island and continent world. Alternatively, the practical impossibility of crossing the extreme interior regions might create feelings of isolation even more profound than those experienced by island dwellers, since the barriers would be environmental rather than simply distance-based. Scientific development on Pangea might have proceeded more rapidly in some areas due to the easier exchange of information and ideas across the unified landmass, while being retarded in others due to the lack of environmental diversity that drives innovation through adaptation to different conditions. The absence of distinct continental faunas and floras might have delayed the development of biogeographic theory, while the extreme climate variations might have accelerated understanding of meteorology and climatology. As we stand at the end of our journey through deep time, surrounded by the familiar landscapes of our modern world, it becomes clear that Pangea has never truly disappeared. The supercontinent lives on in ways both obvious and hidden, its presence woven so thoroughly into the fabric of our contemporary existence that we walk through its legacy with every step we take across Earth's surface. The very ground beneath our feet carries Pangea's signature. The coal that powers our cities is compressed sunlight from carboniferous forests that carpeted the supercontinent's margins 300 million years ago. The oil and natural gas that fuel our transportation systems originated in marine ecosystems that thrived in the warm seas surrounding Pangea's shores. The metallic ores that built our technological civilization were concentrated by geological processes operating during the supercontinent's assembly and breakup. In a very real sense, modern human civilization is constructed from the material remains of Pangea's ancient world. The continental shapes we consider permanent features of Earth's geography are temporary arrangements of crustal fragments that once formed parts of the unified supercontinent. The east coast of North America and the west coast of Africa still bear the complementary scars of their violent separation when the Atlantic Ocean opened. The mountains of Scotland and the Appalachians of eastern North America are fragments of the same ancient range, torn apart by continental drift but retaining their geological kinship across thousands of kilometers of intervening ocean. In the deepest layers of human consciousness, there may lie traces of Pangea that extend far beyond geological evidence. The universal human fascination with maps and exploration, the persistent dreams of discovering lost lands and hidden continents, the mythological themes of separation and reunion that appear in cultures worldwide, all these might represent psychological echoes of our species' deep evolutionary history on a world that was once unified in ways we can barely imagine. The biological world that surrounds us carries Pangea's signature in the genetic code of every living organism. The fundamental biochemistries that unite all life on Earth evolved during the supercontinent's reign, when the absence of geographical barriers allowed evolutionary innovations to spread across global ecosystems. The basic cellular mechanisms that power plant photosynthesis, the respiratory systems that allow animals to extract energy from their food, and the DNA repair mechanisms that maintain genetic integrity across generations all bear traces of their origins in Pangean environments. Modern conservation biology struggles with the legacy of Pangea's fragmentation. The endemic species that make each continent unique are also vulnerabilities, isolated populations that lack the genetic diversity and geographic connectivity that once characterized Pangean life. Today's conservation efforts often focus on recreating the biological corridors that existed naturally when Pangea provided unbroken habitat connections across continental distances. In trying to save modern biodiversity, we are essentially attempting to recreate aspects of Pangean connectivity on a much smaller scale. The plate tectonic processes that destroyed Pangea continue their work today, slowly rearranging Earth's surface in preparation for future supercontinents. The Atlantic Ocean that opened when Pangea split apart is now widening by several centimeters each year, while the Pacific Ocean shrinks correspondingly. In 200 million years, the continents may reassemble into new configurations with names like Pangea Ultima or Amasya. Pangea's story is not a completed chapter, but part of an ongoing cycle that will continue for billions of years. Climate science has revealed that Pangea's influence extends beyond geology into the very atmosphere we breathe. The carbon cycle that regulates Earth's temperature operates over timescales that include the assembly and breakup of supercontinents. The carbon dioxide released by weathering Pangea's mountain ranges, the organic carbon buried in its coal swamps, and the carbonate rocks formed in its surrounding seas all continue to influence atmospheric composition hundreds of millions of years after their formation. In the realm of human culture, Pangea's legacy appears in unexpected places. The universal human response to vast landscapes, the sense of awe inspired by great plains, massive mountain ranges, and endless horizons may reflect psychological adaptations that evolved during our distant ancestors. Existence on a supercontinent where such landscapes were the norm rather than the exception. Our species' remarkable ability to adapt to diverse environments might trace back to evolutionary pressures that operated when climate extremes were continental in scope. The search for extraterrestrial life often focuses on planets that might harbor conditions similar to Earth. But Pangea reminds us that even Earth-like worlds can be almost unimaginably different from our current environment. Understanding how life functioned under Pangean conditions provides crucial insights for recognizing how biology might operate on alien worlds with different continental configurations, atmospheric compositions, or environmental extremes. Modern geology continues to decode new chapters of Pangea's story as analytical techniques become increasingly sophisticated. Each new discovery, whether it's a fossil that reveals previously unknown aspects of Pangean life, a mineral formation that preserves ancient environmental conditions, or a computer model that simulates supercontinent climate systems, adds details to our understanding of this remarkable period in Earth's history. The philosophical implications of Pangea extend far beyond scientific interest. The supercontinent represents a profound example of how radically different our familiar world can be while remaining recognizably the same planet. Pangea reminds us that change, not stability, is the fundamental characteristic of Earth's systems. The continents we consider permanent are temporary arrangements. The climate we consider normal is a brief moment in a much longer story, and the biological communities we work to preserve are snapshots from an ever-changing evolutionary drama. Perhaps most remarkably, Pangea demonstrates the deep connectivity that underlies apparent separation. Though the supercontinent fragmented hundreds of millions of years ago, its influences continue to connect every aspect of our modern world through chains of cause and effect that span geological time. The rocks beneath our feet, the air we breathe, the life forms that share our planet, and possibly even the thoughts we think all carry forward the legacy of that ancient unified world. As we face an uncertain future marked by rapid climate change, biodiversity loss, and environmental disruption, Pangea provides both sobering perspective and surprising hope. The perspective comes from recognizing that Earth has experienced changes far more dramatic than anything currently threatening our world. Yet life has not only survived, but flourished and diversified in ways that seem almost miraculous. The hope comes from understanding that the same geological processes that created Pangea's extremes also created the conditions that allowed life to achieve unprecedented complexity and beauty. The memory of Pangea lives on in every sunset that illuminates sedimentary rocks formed from the supercontinent's erosion, in every fossil that preserves evidence of its remarkable life forms, and in every new discovery that reveals another aspect of its extraordinary story. In learning to read these memories written in stone and preserved in the genetic code of living organisms. We not only satisfy our curiosity about the past, but gain crucial insights for navigating our planet's future. Pangea's greatest gift to our understanding may be the recognition that Earth is far more dynamic, resilient, and creative than we typically imagine. The supercontinent story encourages us to think in longer timescales, to recognize the deep connections that unite apparently separate phenomena, and to appreciate the remarkable creativity of geological and biological processes operating across vast spans of time. If you've found yourself transported by this journey through deep time, if you've felt the wonder of standing on that ancient cliff, overlooking a world so different, yet so fundamentally connected to our own, then perhaps you understand why the story of Pangea continues to captivate scientists and storytellers alike. The supercontinent represents one of the most remarkable chapters in our planet's biography, a reminder that Earth's capacity for transformation and renewal extends far beyond human timescales into realms of change that challenge and expand our understanding of what's possible. In the end, Pangea's story is also our story, written in the rocks beneath our feet and encoded in the very atoms that compose our bodies. Understanding this ancient world helps us better understand our own place in the vast sweep of geological time, reminding us that we are not separate from Earth's history, but active participants in a story that began billions of years ago and will continue long after our species has joined the fossil record. The memory of the Earth is also the memory of ourselves, preserved across deep time in languages written in stone, ice, and the genetic code of life itself.